Se è leggero va bene. Sa, prova 1, 2, 3, 4. Ciao, eccoci, benvenuti. Ciao, ciao, ciao. Eccoci, eccoci. Bene, bene, bene. Prova, prova, prova. Sì, 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 prova, prova. Sa, sa, prova. 1, 2, 3. Sarà sa, sa, sa. 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 Prova 1, 2, 3. Prova 1, 2, 3. Prova, 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 prova. Ok. Quindi questo c'è.
Proviamo l'archetto.
Sì, archetto. Senti, questo glielo do a loro.
Sì, ma qui ragazzi ci devono aprire la diffusione.
Sì, infatti.
Sì,
Non l'hanno divisa ancora, mi sa, ragazzi.
sì, sì. E va bene. Anzi, un po' troppe alte, facciamolo più medioso.
Che avrebbe detto che non era possibile mandare. Solution could be to put the mic.
You talk with this, you can.
You have so to select audio device
That's what I'm
speakers.
going to-
Sì, dal PC va bene. Ehm, sì, ma se non mi sbaglio gli esce solo l'HDMI. Sì, sì, ma gli esce. Però poi non va... Esatto. suonato. Ha detto che sta scrivendo al tecnico.
Vabbè, su questo sì.
Se non ti dispiace, parlo io e te lo passo. Vabbè, così ti posso presentare in qualche modo o semplicemente Francesco?
Come vuoi.
Francesco? No, perché... Ok, stai parte di qualche università, qualche azienda? Ah, ok.
Tanto poi mi presento pure io.
Madonna, apriamo la giornata.
Stella, ce l'hai queste?
Sì, grazie.
Ce le hai? Ok.
Sì, grazie. E quindi sta riversando tutto su di noi. Questa è anche la mia prima volta con Python. Come sta?
Come vado? I capelli stanno bene?
Sta a posto. Mi dispiace per l'occhio. Dobbiamo riprovare. No. Non tocca niente. Figa questa,
Non voglio che mi si taccia per Berlusconiano.
No, è meme. È meme. Ah, c'hai tutta la squad qua, eh? C'è tutta la squadra. Ok.
I miei fan.
Ok, noi dovremmo iniziare, se no mi dispiace, ti faccio uscire fuori tempo. Aspetta, te lo dico. Sì, siamo... Sì.
Ma il gelato l'archetto era acceso?
Sì, penso di sì, la vicina accesa. Sì, sai, tanto parlato con questo.
Hello. It's too early. Wait.
Okay, so hello everybody, welcome to the first talker of the day in Gnocchi. Well, this is Francesco from Prima, and Francesco, the stage is yours.
Thank you very much. Can you hear me right? Yes, I think you can, because I can hear myself as well. Well, welcome to Working with Data Scientists and Why I Left My Job. Well, the first thing I want to do today is introduce myself. My real name, so the name my mom gave me is Francesco. But, you know, in my company, everybody calls me Frango. So feel free to call me Frango if you like. I work with Python, as you probably do as well. And I've been working with Python for almost 8 years now, which is quite a long time, I have to say. And currently, I work as a machine learning engineer in a company called Prima. We have a delegation from Prima here. We're also sponsoring this conference. And we have a stand outside. I don't know if you've seen it, but if you want to come and talk to us. And if you're looking for a job, go to this website, and you'll find all the open positions that we have. We are an insurance company, but even though we are an insurance company, we really care about tech. And I have to say we have a very strong tech culture. So you'll feel welcome in Prima if you like to come. And we are hiring in Italy, Spain, and the UK. And Prima is also sponsoring my presence here, so thank you, Prima, again. It's also paying my salary, so thank you twice. All right, now, the big question. Did I really leave my job because of data scientists? Well, the title was kind of a clickbait title, and the answer is no. And actually, it's quite the opposite. I've been working alongside data scientists for about 3 years now, because 3 years ago, in Prima, we had a problem with data scientists. Well, you know, they weren't working, well, I mean, they were working well, but not so well from the perspective of a software engineer. So we thought, why don't we create teams made up of data scientists and also engineers? So we created cross-functional teams with data scientists and machine learning engineers. And I have to say, in hindsight, it worked really well. And now we have a bunch of machine learning engineers in Prima, and we also have several teams adopting this practice. And let me smile for the camera. Hello. And what I was saying. And it worked really well. And I consider this presentation kind of the summary of what I learned in this experience. What I learned about data scientists. Surely I learned that they are very smart people. But sometimes, you know, they kind of do it wrong. And and today I want to consider with you 3 practices that are very common in the world of software engineering: version control, testing and, in general, checking the quality of your code. And this is something that, you can ask ourselves, are data scientists doing any of this? And why aren't they? And okay, we'll consider each and every one of these, and we'll ask ourselves the question. All right, so let's start with the first one. What is version control? Now, most of you probably know what version control is, but I just want to give you some perspective. So if you're working in a big team and you have many people working on the same code, you're going to have a lot of changes all over the place, right? So you want to be able to keep track of what is changing, who is changing something, and when the change is happening. And this will enable you to collaborate fairly easily, because you want to be able to review the changes, accept them or reject them. You want to be able to resolve conflicts. So if people modify the same code at the same time, or code that depend on other code, you'll be able to resolve this. And this, luckily, is a solved problem in software engineering. And the thing that everybody uses is Git. Virtually used by everyone. There are other systems, but no one knows about them. So you should be using Git. And when you use Git, you should be aware of its downsides, because every technology has its downsides. And I would say the downsides of Git are mainly two. It can get kind of complex. If you have a huge code base, you have many people working, and you have a long history of changes. So you really have to know what you're doing. And there are some risks with Git. I'm sure each and every one of you have seen someone push credentials or secrets to Git. And that's very dangerous, and it happens to data scientists in particular. All right, now the big question. Are data scientists doing version control? Well, I have a meme for you here that shows the way they generally do version control. And so we have a notebook, and the first one, the original one, is untitled.ipynb, and then you see this notebook being copied over and over again, and just the suffix changes. So you have the copy 1, then you have the copy 1 final, but then you also have the copy 2. So it was not final after all, right? And so I think, of course, this is not a great way to do version control, because you're going to have versions being shared across people and sent over weird channels. Like, for example, I've seen data scientists share these versions through Google Drive, which, is not ideal. And so it's going to become a mess. Keeping track of the changes, keeping track of what happens is very hard. You're going to have duplicated code all over the place. So, you should be using Git instead. All right, let's move on to the second one, testing. What is testing? I have to say I found this really nice and general definition on Wikipedia. And it says, software testing is the act of checking whether software satisfies expectations. So I really like it. It's very general. And of course, the bare minimum expectation you would require from your software is that it runs correctly and produces the right output given an input, right? And you can check that. You can check that with testing. In Python, we use generally PyTest or unit test or something like that. And ideally, you want to be able to assess if you make a change that shouldn't change the behavior of your code, you want to be able to quickly assess that your code didn't change. And so you want to be able to test frequently, automatically, and quickly. And again, as in the case of Git, there are some downsides here, because testing can get complex, right? Because you have additional code compared to the code that actually runs, and you're going to have to maintain that code, and that can be complex and costly sometimes. But still, people really like testing because it improves their confidence in their code, improves their confidence that their code is correct. And now, again, the question. Are data scientists testing their notebooks? Well, I have another meme here for you. I'm not going to read it, but you can read it. And I don't know, if you were to take a notebook out of a data scientist code base and just try and run it, would that run? I don't know. Well, in my experience, on average, it doesn't. And there are a lot of reasons. For example, you might have dependencies problems. So you just run the first cell and pandas won't import. Or maybe the order of cells is weird, because you were supposed generally to run a notebook from top to bottom, but you know very well that's not the case, because maybe you have to change a cell in order to make the notebook run. So in my experience, most of the time, notebooks are not reproducible. And of course, that is not great, right? Because we're doing data science, and so it's science. And I've learned at school that one of the cool things about science is that it should be reproducible. And often that's not the case in data science. All right, one last practice, code quality checks. This is something a bit different. So your code might be correct. So it might be producing the right output, but your code might be unmaintainable. So if making a change to your code is very costly and it's unfeasible, it means that your code is unmaintainable. So you should care also about non-functional requirements of your code. And we have two families of code quality checks we could do. The first one on the left is styling and formatting. So you want your code to look good. And why would you care about that? Because if your code looks good and has a consistent styling, people are going to be able to work on that easily, right? And luckily in Python, we have a formatting standard called PEP8, which stands for Python Enhancement Proposal 8. And we have a bunch of tools like Black, AutoPEP8, and Rough that will check the code and will tell you if the code adheres to that standard. And if it doesn't, you just run these same tools and they will fix the code for you. So it's very cheap, you can run it quickly, and it will fix the code for you. So why not adopt it? And on the right instead, we have linters. Now, this is a different family of tools. They will try to look at your code statically without running it and check if the code satisfies certain standards. For example, they check if you have unused code. So if you have a code that is not being used by anyone, why would you keep that code there? So they're going to tell you, you have an unused function, get rid of it. Or maybe you have duplicated code. So they will tell you, and you could extract that code into a function. So they will tell you a lot of interesting things about your code, and you're going to have to fix them manually. So it takes a little bit more effort compared to formatting, but it's still, I think it's still worth it. And now again, the same question as before. Are data scientists doing any of this? Well, in my experience, sometimes they don't even know about this. I mean, they might know about formatting, but not about linting. And so I think they should. So if you agree with me, and if you think you're a data scientist, or you are a data scientist, and you are not doing any of this, and you think it might be worth looking into it, I want to give you a recipe, a series of steps to follow to make this happen. Okay? So let's first start with the first step. And this might be obvious, but it's not. And it's to educate. So educate people, and if you need to be educated as well, educate yourself. And the reason you need education is often that data scientists come from a different background from software engineering. And of course, that's perfectly fine. I also come from a different background, and they are very smart. I am smart, and they are also very smart. And especially people coming from the sciences, they are very smart. But, you know, they come from different backgrounds, so it might be that they haven't been exposed to these practices. So they have to learn about it, and I think learning about it also uncovers the value of these tools. Because, you know, what happens in the world of software engineering, and we have to be fair because that happens, is that software engineers try to push things to people, right? Especially when they are best practices. But I think there's value in the practices we consider today. And if you learn about them, you'll see the value. So it means that data scientists and engineers are going to be on the same page, and that's what you want. Now, the second step, this is a little bit more technical. It would probably require its own presentation, but I wanted to mention it because I think it's very important. And it's the idea of moving away from notebooks. Now, if you really like notebooks, sorry, I don't like, I mean, okay, I have to say that they're nice. So notebooks are very nice. They're really shaping the world of machine learning and AI. But from the perspective of a software engineer, they kind of encourage bad practices. And I think the main reason is that a notebook is something that is supposed to be all in one place, right? So you have the code itself and also the output in this nice IPyNB file. I don't know if you ever looked into this file, but it's basically a JSON file with code and crazy outputs. And I think this encourages bad practices. In particular, it incentivizes you to have all the code in one place. So it's hard to extract code that should be reused across notebooks. So I think you should be trying. Oh yeah, there's also another point. Sorry, I forgot about that. And the second point is that IPyNB file it doesn't work really well with Python tooling. So the tools that we mentioned earlier, Black, Rough, and whatever, they all work on Python modules or Python packages, so they don't work as well with IPyNB files. So if you agree with me, if you think this makes sense, I think you should try and move away your code from notebooks and just keep the code that really needs to be in the notebook. And maybe you could package your code so you can reuse it across notebooks. All right, so if you agree with me, if you're educated, you're a data scientist, if you don't like notebooks, just like I don't like them, now it's time to adopt. And this is a critical phase, I have to say. And the critical part of it is to do it gradually. You know, in the world of software, we are always tempted to do what is called greenfield development. So if you're in front of a messy code base, and I don't know, you want to test it, well, you're going to be thinking, well, let's rewrite everything from scratch. But I suggest not doing that, because it's going to take you a long time to have working code. So instead, do a gradual adoption and move things out of the messy code base gradually, so you keep having working code. And in doing this, never forget the impact and effort analysis. So if there's a particular notebook that is critical and needs to be tested, so you're going to have to migrate that one first. And also remember that it's going to take you time and effort, so always consider this trade-off. And include the data scientists. So if you, like me, are a machine learning engineer in a team of data scientists, you have to include them in the planning phase and also in the adoption phase. Particularly in the adoption phase, you want them to help you. They've learned about this technology so they can practically help you and they can see the value of this technology. Now the step 4, which is, I think, probably one of the most important ones, is to make it fun. There are 2 ways I wanted to talk to you about. And the first one is memes. We've seen some memes during this presentation, and you also laughed, which is very kind of you. And but I think the reason why you laugh when you see memes is because memes, you see yourself in memes, or you see someone else in those memes. So you recognize something in those memes that they make you laugh. So why not do memes about what you do at work? So if something fun happens at work, turn it into a meme. You're going to get a lot of karma, and also you're going to make people have fun. And, you know, work sometimes is very hard. So just let's make it fun. And the second tool I wanted to mention is gamification. So this is the idea of turning something that it's not a game into a game through the elements of rewards and milestones, you know, the kind of things you would find in a game. And I've got a very nice example, I think, here. It comes from PyLint. I don't know if you ever run PyLint, but let's suppose that you run PyLint on your code base, and everything is fine, so your code doesn't have any problem. PyLint will print your code as being rated at 10 out of 10, which is pretty cool, you know. Thank you, PyLint. And I see this as kind of a gamification element, because it gives you, the little boost of confidence. Maybe you've been trying to fix the PyLint errors for an hour, and then you get this nice rating on your code, which is nice. And we expanded on this a bit, because we also added a beautiful thank you for linting ASCII art with different arts depending on the repo. You know, something very silly and something very cheap. But I mean, it's nice when you see it. And finally, the final step, don't leave your job. So don't give up. I know it can be messy, but really, when you take data, when you mix it with the intelligence of data scientists, and you also add the rigor and practices of software engineering, that's when the magic happens. That's when you really uncover the value of data. And that was it. Thank you very much. Now it's time for some Q&A. Oh, yeah, there are questions. Good, very good. Plenty of questions.
Thank you, Francesco. So, let's see.
Thank you.
Yeah, because the first question was already answered by the slide on the notebooks. So given that you abhor notebooks in production, I imagine that in Prima, as in many other companies, you use a platform that has to do with the bricks. So my question was how much and how do you approach the fact that some part of the code will be strictly running on this platform, and how much of the code is external or agnostic in terms of execution, testing, and deployment? So thank you.
Very nice question. Yes, we do use something that ends with bricks in Prima. That's Databricks. And yeah, the situation that we have now is that we don't put notebooks into production. So no code that is a notebook goes to production. And we have dedicated repos and services where we put the output of notebooks. So data scientists are working on notebooks on Databricks in our case. And the output of notebooks are generally artifacts, so models or anything that's relevant in machine learning. And then we encapsulate it in dedicated services, and we pay a lot of attention on the quality of the code that goes to production, so we keep them separated. I think it's not perfect because there's some separation that really doesn't make sense because it's basically the same code, and I think it should be in one place, but it's not easy to make it work. And so at this point we are in this compromise phase. But I hope that we're going to push to the direction where we have everything in one place and we have a one-to-one relation with one repo for everything basically. So notebooks corresponding to services. I think that's the way to go.
Okay, just a quick question. Among your team here, is there any of the data scientists that can confirm, or maybe we can hear the other parts of the story?
No, I can confirm that everything that Franco said is true. And now there is a lot of value in having both machine learning engineers, data engineers, and data scientists in the same team. It's a huge value. We went through a phase in which this was not the case in Prima, but then everything, as Franco said, exploded as soon as we embedded both engineers and data scientists in the same team. Yeah.
Data scientists always stealing questions. No, I'm joking.
Thank you. So,
Thank you. As a data scientist, I can confirm, I think. No, just two quick questions. You mentioned in your slide code review.
Yes.
I wanted to ask you how you do it and what issues have you found with it. And second, how do you force data scientists to use, I don't know, pre-commit hooks or something to force them to use linting and similar?
You just force them? No. Well,
Except forcing.
Let's go with the first one. Code review. Well, we do it the way that generally people do it. We have a Git repo, and we have branches, and we require code to be reviewed before it gets merged into the main branch. So master, and well, the challenges that we've found is that you have to repeat a lot of the times because, well, let me explain. So generally, initially, it was just machine learning engineers doing review to data scientists. But now these things is slowly changing because now data scientists have learned a lot and they're more comfortable, and we also don't want to be overworked as engineers. So we require data scientists to be able to do review themselves to each other and also to our code. And we require review, so we need at least one approval to merge into master. So that's kind of standard in the industry. And to answer the second question, how do we force them? Well, the way you force them is using continuous integration and pipelines. I don't know if something you've heard about, but when you work with Git and you use a platform like GitHub or GitLab, you can so you can introduce some automation. Every time you push something to a branch, or every time you want to merge something into the main branch, there's some pipelines that are going to run, and they're going to check your code. For example, you could be checking that your code is correctly formatted, and if it's not, I'm sorry, you can't merge that PR. So we require that to be done. And then, of course, if you are trying to merge a PR, you're going to have to fix the code. So that's basically the way we do it.
Okay, thank you, Francesco. Sorry, another question for you.
Yes.
Yes, thank you. It's a really good presentation, first of all.
Thank you.
I'm guilty of being a data scientist, probably started with really bad practice at the really beginning, but I agree with you. I think definitely move to a more standardized software development, like frameworks is paid a lot. But there is, from my perspective, always a pain in this game, which is actually testing. So essentially, my question is about how you approach testing when you have to test a really expensive object like a model or an inference of a model that is not actually quite as easily predictable, easily built up like a normal software engineer testing. Thank you.
Oh, yeah, that's a very good question. Yes. Yeah, testing in the world of data science is particularly complex, because what you're trying to do is first you want to kind of test notebooks, as we said. And there's one problem with notebooks, that they generally take a long time to run. So, and the main reason is that they ingest a lot of data. And what you want to try to achieve, at least this is what we do in Prima, is try to mock data. And the concept of mocking is something for which you try to, if you have in your test, if you have some expensive operation, you're going to try to fake it during the tests. And that's going to make your tests run quickly. And so we mock data. So we try, of course, it has to be a realistic data set, but a very small one. So we can mock it, and then we try to run notebooks from top to bottom and see if they produce the right output. As far as models are concerned, it's basically the same thing. Of course, a model is something complicated because it produces a distribution of outputs. So if you want to really test the model, you should be testing the distribution of the output. What we do is we test the model point-wise. So we always check that the output is what we expect on, 5 to 10 points. So that gives us some confidence that the model is correct. And also, you always have to think about that a model is, in itself, is just like a function, but it is in a bigger context, right? And in our case, the context is pricing. So in the end, what we care about is that prices are correct. So we check on that, actually, instead of checking. Well, we also check the model in itself, but we care about the overall output of the thing. I hope that answers the question.
Yes, thank you. Thank you, Francesco. So, everybody, we are run out of time. So, if you have some other question, you can ask during the coffee break.
Yeah, I'm happy to socialize, as you can see here. So,
good,
come and talk
Francesco.
to me.
So, thank you, Francesco.
Thank you.
So.
chiedere solo una cortesia. Dalla regia ci dicono che riescono ad inquadrare bene lo schermo e te vicino al leggio. Quindi se ci spostiamo poi vai fuori.
Sì, vabbè, mi sposterà per bene, basta.
Ok, nel senso che. Ok, dai.
Guarda, meglio se lo collega la presa? Meglio se lo collega la presa? Penso lui.
Io tra un minuto te li faccio subito. No, perché se vuoi la presa la mettiamo subito. La possiamo attaccare e tu te la tieni qua, così se vedi che si sta scaricando attacchi. Così vai più. Non ti preoccupare, vieni qua. Allora facciamo così. Vai, vedi se è tutto a posto. Andiamo in onda. Hello everybody. So, welcome to the Gnocchi room, our speaker Antonio. And well, I will tell you something. If you have some question for our speaker, I will kindly ask you to reach the speaker during the breaks, okay? Well, now let's see what Antonio will say. So Antonio, take a break.
Grazie. Buongiorno a tutti e benvenuti. Quest'oggi parleremo di design by contract e di come costruire software robusto con il contract first development. Mi presento, sono Antonio Spadaro, ma potete trovarmi online come I Love Linux. Sono un DevOps engineer per Partech, sono un programmatore competitivo e ovviamente sono un entusiasta utilizzatore di Python. Partech è lo sponsor di questo talk. Siamo un'azienda di più di 200 persone, ci occupiamo di infrastrutture cloud, AI automation, cyber security e servizi finanziari. Quelle che vedete qui sono alcune delle conferenze a cui siamo parecchio affezionati, a cui partecipiamo praticamente ogni anno. Questi invece sono i nostri partner, alcuni dei nostri partner. E infine c'è la nostra rivista YAM, dove cerchiamo di mettere nero su bianco parte delle nostre esperienze. Prendiamo un argomento e scriviamo quello che abbiamo imparato a riguardo, nella nostra esperienza. Bene, quest'oggi introdurremo innanzitutto i contratti, poi parleremo del design by contract e del contract first development. Vi presenterò inoltre 2 casi di studio su come il contract first development ha aiutato il processo di sviluppo. Iniziamo dal design by contract. Per introdurre il design by contract bisogna partire dalla logica di OR. La logica di OR è un set di regole di assomi formale per verificare la correttezza di un programma. Nel momento in cui quindi queste regole vengono soddisfatte, potremmo dire che un programma è formalmente corretto. Tra queste regole, quella che a noi ci importa è la tripla UR, che è definita così. P e C sono delle asserzioni, quindi sono delle condizioni che noi vogliamo soddisfatte. P in particolare sono le precondizioni di un comando, C invece sono le post-condizioni. La tripla UR dice che se l'asserzione P è vera, allora il comando verrà eseguito e dovrà soddisfare l'asserzione Q. Vedremo meglio questo in un esempio più in là. Il design by contract, quindi, vuole, in altre parole, formalizzare il codice. Lo scopo di formalizzare il codice è di spiegare, tra virgolette, come funziona. Lo facciamo usando delle precondizioni, delle postcondizioni e delle invarianze. Quindi, le precondizioni sono quelle condizioni che devono essere soddisfatte prima dell'esecuzione del comando, del codice o della funzione. Le postcondizioni sono quelle condizioni che devono essere soddisfatte dopo l'esecuzione del comando. Quindi possono essere controlli dell'output, possono essere controlli dell'ambiente. Le invarianze invece sono quelle condizioni che devono essere soddisfatte durante tutta l'esecuzione dell'output. Per questo si chiamano invarianze, perché non devono variare durante tutta l'esecuzione. Nel formalizzare il nostro codice potremmo utilizzare anche altri strumenti, come ad esempio la descrizione dei side effects, degli errori e delle eccezioni, o addirittura, ma lo si fa raramente, descrivere il codice in termini di performance, quindi descrivendone la complessità computazionale in termini di tempo o di memoria. Però sono casistiche un po' più rare. Un esempio di codice in cui applichiamo il design by contract è quello che vedete qui. Il nostro obiettivo in questo codice è formalizzare le precondizioni e le postcondizioni di una data funzione. Questa funzione prende in input un tempo t, che è una stringa, data da ore e minuti, ad esempio le 11:45 all'inizio di questo talk, e ne fa il parsing, restituendo una tupla di 2 elementi. Il primo elemento sarà l'ora, il secondo elemento saranno i minuti. Se passiamo 11:45 avremo come output una tupla il cui primo elemento è 11 e il secondo è 45. Fin qua tutto semplice. Abbiamo delle precondizioni perché il nostro comando abbia senso di funzionare. Ci aspettiamo che t, il dato in input, sia una stringa. Dobbiamo verificarlo poiché Python non è fortemente tipizzato. Ci aspettiamo inoltre che t abbia un determinato formato. In questo caso la regex che vedete include tutti i formati, tutte le ore dalle 00:00 alle 23:59, escludendo ovviamente orari che non hanno senso di esistere, come le 15:72. Se queste condizioni sono soddisfatte, allora eseguiremo il nostro codice. In questo caso è la riga 9. Salviamo il risultato. Controlliamo a questo punto se delle post-condizioni sono soddisfatte. Quali sono le post-condizioni? Il risultato deve essere una tupla di 2 elementi. Questi 2 elementi devono essere degli interi, le ore devono essere comprese tra 0 e 23 e i minuti compresi tra 0 e 59. A questo punto restituiamo il risultato. Cosa succede? Se noi abbiamo soddisfatto sia le precondizioni che le post-condizioni, sappiamo che il chiamante ha chiamato la funzione correttamente. Avendo chiamato la funzione correttamente con dei dati che ci aspettiamo di ricevere, allora la riga 9 dovrebbe funzionare. Se la riga 9 funziona correttamente, le post-condizioni devono essere anche soddisfatte, perché se ho in input un tempo del formato giusto con le ore giuste, allora in output devo avere anche formato giusto e ore giuste. Questo non ci permette di verificare che a un dato input corrisponde un dato output. Verificare che se io do in input 11,2.45, allora ho in output 11,45, una tupla di 2 elementi, è compito dei test. Questo però ci permette di verificare che durante l'esecuzione del codice, sia durante i test, sia durante le fasi di sviluppo, di collaudo, e magari anche in produzione, il codice stia ricevendo in input i valori giusti e stia dando in output i valori giusti, che quindi rispettano quello che abbiamo formalizzato, e cioè il contratto. Perché abbiamo usato degli assert? Il problema dei contratti, una critica che potrebbe essere avanzata, è però sto eseguendo righe di codice in più. Righe di codice che in questo caso erano abbastanza semplici, a parte le regex che potrebbero essere un po' più complesse, ma a volte la verifica dei contratti potrebbe essere parecchio più complessa e potrebbe quindi diventare computazionalmente esosa. Se stiamo sviluppando un programma che è performance sensitive, dove quindi dobbiamo curare le performance perché ad esempio vogliamo un throughput che sia il più largo possibile, allora potremmo dire, sai che forse i contratti mi rallentano il codice. Usando gli assert però noi possiamo disabilitarli facilmente passando il parametro "-" maiuscolo all'interprete Python. L'idea qual è? L'idea è che noi avremo i contratti attivi durante le fasi di sviluppo, durante i test e durante le fasi di collaudo. Ma qualora l'applicazione sia performance sensitive, potremmo disabilitarli in produzione. Nonostante tutto, avremo verificato che il codice sembra soddisfare i contratti durante tutte le altre fasi di ciclo del software. Una cosa che potremmo fare nel caso in cui volessimo mantenere comunque attivi i contratti è, se abbiamo un'applicazione distribuita su 10 nodi, potremmo mantenere comunque un nodo in modalità di debug, tra virgolette, e quindi con gli assert attivi. Ogni tanto leggerà una richiesta, sarà più lenta a processarla, ma verificherà che i contratti siano soddisfatti. Oppure disabilitiamo tutto in produzione e si riattiva nel caso in cui si pensa ci siano problemi. Questo è un altro esempio. Il focus vuole essere sulle invarianze, che vediamo definite alla riga 14. La classe descrive un orologio con ore e minuti. Le invarianze sono quelle condizioni che devono essere sempre soddisfatte durante tutta l'esistenza della classe. Le controlliamo infatti dopo l'inizializzazione e durante la chiamata della funzione tick. Le invarianze quali sono? Ore e minuti devono essere interi, devono sempre essere interi. Ore deve essere compreso tra 0 e 23, altrimenti c'è un bug. Minuti devono essere compresi tra 0 e 59, altrimenti c'è un bug. O è inizializzata nel modo sbagliato. Le invarianze le controlliamo alla riga 8 perché controlliamo che l'input sia corretto. Le invarianze le controlliamo inoltre alla riga 22 e alla riga 27 della funzione tick. La funzione tick, per la cronaca, aumenta di 1 minuto l'ora dell'orologio, nulla di straordinario. Tuttavia controlliamo che la funzione e la classe sia valida, controllando le invarianze, e quindi, dato il contratto che abbiamo definito, la funzione, la classe continua a soddisfarlo, e che dopo l'esecuzione della funzione tick le condizioni siano ancora soddisfatte. Se la funzione tick, la riga 25, fosse implementata male, ce ne accorgeremmo. Magari avremo un float a un certo punto, magari potrebbe non importarci, ma da contratto dobbiamo avere degli interi. Questo ci permette di assicurarci che tick non solo incrementi di 1 minuto, ma che mantenga anche la tipizzazione e gli standard del contratto. Ricapitolando, quali sono i vantaggi del design by contract? Innanzitutto abbiamo un miglior design del codice, in quanto stiamo prima di tutto formalizzando le precondizioni, le postcondizioni e le invarianze, quindi tutte quelle che sono le esigenze del nostro codice, che sia una funzione, una classe, un'interfaccia o un'API. Dopodiché, nel momento in cui noi stiamo formalizzando le esigenze del nostro codice con delle condizioni booleane, noi siamo sicuri che quando un'altra persona andrà a lavorare su quel codice, riuscirà facilmente a comprendere quali sono le esigenze di quel codice. Se scrivessimo sulla documentazione, guarda che ore e minuti devono mantenersi degli interi e devono essere compresi tra 0 e 23, sarebbe chiaro. In altri casi la documentazione potrebbe essere un po' a libera interpretazione. Con delle condizioni booleane questa cosa non succede. Infine abbiamo una migliore robustezza e affidabilità del codice, perché nel momento in cui noi validiamo il contratto durante tutte le fasi del software, magari anche in produzione, e nel momento in cui abbiamo quindi dei controlli in più, oltre ai test, e proviamo a far così e vediamo cosa succede, siamo ancora più sicuri che il codice funzioni, e siamo anche sicuri che se c'è qualcosa che non va, il codice smetta di funzionare, anziché continuare l'esecuzione e potenzialmente creare dei problemi. Passiamo ora al Contract First Development. Il Contract First Development aggiunge una cosa, l'ordine temporale. Noi vogliamo infatti che prima di iniziare qualunque implementazione del codice venga definito un contratto, venga dunque formalizzata l'implementazione. Vedremo ora perché può esserci utile. Partiamo da un esempio. Abbiamo uno stakeholder che vuole X e uno sviluppatore che deve svilupparlo. Questo è l'esempio in cui non usiamo dei contratti. Quindi lo sviluppatore recepisce cos'è X, prova a svilupparlo, a un certo punto dice guarda, penso di aver finito, facciamo una demo. Mostra la feature al cliente, la testano, il cliente fa qualche domanda e ci sono due possibili output. O il cliente non è soddisfatto e si ricomincia modificando il codice, riscrivendolo, riadattandolo, oppure il cliente è soddisfatto. Ora, scrivere codice è lento, quindi riadattare codice richiede tempo. E anche qualora invece il cliente fosse soddisfatto, poiché non abbiamo formalizzato quali sono le esigenze del cliente per X, allora il cliente, che durante la demo ha visto una parte di quello che è X, una parte di come funzionava, poi nell'usarlo, magari in collaudo, magari in produzione, potrebbe accorgersi che alcune cose non vanno come pensava che andassero, o che alcune cose magari mancassero totalmente. Secondo esempio, qui è lo stesso esempio di prima, soltanto che anziché fare una demo con il cliente, diamo principalmente il contratto da revisionare. Per cui noi scriviamo il codice, lo formalizziamo e diciamo al cliente: guarda che noi abbiamo fatto questo, non te lo facciamo vedere, ma ti spieghiamo nel dettaglio, formalizzato appunto, cosa abbiamo fatto. In questo modo il cliente potrà revisionare un documento che è un po' più formale e potrà dire o no, non va bene, e allora riscriveremo il codice e ricreeremo il contratto che formalizza il codice, oppure potrà dirci sì, va bene, e a quel punto saremo sicuri che il cliente ha abbastanza sicuri, la sicurezza poi è un po' difficile, che il cliente ha ciò che vuole. Abbiamo quindi un livello di sicurezza maggiore. Il problema è che nel momento in cui il cliente ci dice no, c'è qualcosa che non va, nonostante possa indicarci nel contratto cosa manca o cosa deve essere diverso, e questo ci aiuta con gli sviluppi, noi impiegheremo comunque del tempo a riscrivere del codice, a modificarlo, parti di codice dovranno essere riadattate, parti di codice verranno buttate, altre parti verranno create nuove. Quindi perderemo ancora del tempo. Caso in cui siamo contract first, noi, prima di iniziare gli sviluppi della feature, formalizziamo quello che sono le esigenze del codice, quindi quelle che sono anche le esigenze del cliente, perché noi scriviamo il codice per il cliente. Quindi, nel momento in cui il cliente revisiona il contratto, ci dice questa cosa non va bene, questa cosa non va bene, allora potremo modificare il contratto e revisionarlo. Ci sono alcuni casi in cui lo stakeholder è una persona tecnica e il vantaggio è che quindi il contratto si può anche scrivere a 4 mani. Ci si mette in call e si dice ok, io ho bisogno di questo, io posso darti questo, si trova un compromesso, si definisce un contratto. Una volta definito il contratto si iniziano gli sviluppi, quindi implementeremo il codice esattamente per quei requisiti, lo scriveremo una volta e risponderà esattamente alle esigenze del cliente. Ci potranno comunque essere dei bug, perché come abbiamo detto il contratto non ci garantisce che non ci siano bug, però avremo una maggiore certezza che il codice funzioni correttamente e avremo risparmiato tempo evitando di riscrivere soluzioni che avevamo pensato fossero soluzioni ma che non lo erano e di riadattare codice che non era scritto per quella cosa, però ormai era scritto, quindi usiamolo. Vediamo ora alcuni esempi. Primo esempio, caso studio in cui abbiamo un progetto che è un progetto full stack. Questo è una cosa che mi è capitata ed è la prima volta che io mi sono approcciato al mondo dei contratti. Non sapevo si chiamassero contratti. Cosa succede? Dovevamo sviluppare una dashboard per un cliente. Io ero nel team di back-end. La dashboard era piena di grafici, quindi quello che trainava lo sviluppo era il front-end che ci diceva noi facciamo questo grafico così e abbiamo bisogno di questi dati. Il problema è che il front-end era contract first, il back-end non lo era. Cioè, lo sviluppo era, il front-end chiedeva che venisse implementata un'API. L'API veniva implementata, il framework di back-end generava i contratti, quindi l'open API dell'API che descriveva l'endpoint, la richiesta, cosa voleva in input, cosa voleva in output. Dopodiché il front-end generava automaticamente delle componenti per comunicare con il back-end e per comunicare con quella specifica API. Il fatto è che il team di back-end in quel momento era estremamente pieno di cose da fare, per cui a volte il team di front-end non poteva continuare con gli sviluppi, perché non aveva l'API, non sapeva come gli sarebbero arrivati i dati. Sapeva di dover realizzare un grafico a barre, ma non sapeva poi come doveva implementare la business logic. Ho pensato, perché non definiamo un contratto? Cioè, se voi avete bisogno di X, noi ve lo diamo, quando riusciremo a implementarlo, perché per ora dobbiamo fare altro. Però sentiamoci mezz'oretta in call, vediamo un po', voi che ci dite le vostre esigenze, quindi cosa vi serve avere, in che formato. Al contempo il back-end sa quali sono le esigenze del database per recuperare i dati, quindi in mezz'ora si definiva il contratto, tale per cui la richiesta poteva essere fatta al back-end con i giusti dati e il front-end al contempo aveva i dati da mostrare a grafico. Il vantaggio di questa soluzione è che nel momento in cui il contratto veniva definito, il front-end poteva tranquillamente creare un mock che rispettasse il contratto e utilizzare un mock per gli sviluppi. Nel momento in cui utilizzi un mock che rispetta un contratto che verrà rispettato anche dal back-end, tu sai che quello che stai testando non è un'idea, è effettivamente quello che verrà implementato. Solo che l'implementazione di front-end e back-end può avvenire in parallelo, in modalità totalmente asincrona. Dopo che avviene l'implementazione sia di front-end che di back-end, l'ultimo step è quello di non usare più il mock e collegarsi alle API di back-end. Testare quindi le API di back-end e vedere che tutto funzioni. Possono esserci dei bug. Il back-end può non gestire bene alcune richieste, il front-end pure, alcuni output. Tuttavia sappiamo che i dati saranno nel formato richiesto e questo ci permette quindi di risparmiare tempo e parallelizzare gli sviluppi. Secondo caso studio. Avevamo bisogno di sviluppare uno strumento che, dati dei file JSON in input, generasse dei file di output. Il problema è che questo strumento non veniva usato da noi l'abbiamo soltanto sviluppato. Lo abbiamo dato al cliente, che a sua volta l'avrebbe fatto utilizzare ad altre persone ancora. Il problema è che i file JSON in input noi li volevamo in un determinato modo. L'abbiamo spiegato al cliente, il cliente ha recepito, tuttavia, come ben si sa, il telefono senza fili non funziona. Per cui nel momento in cui queste informazioni passavano ancora a chi doveva usare poi effettivamente il tool, spesso i dati in input non erano quelli corretti. Quindi abbiamo pensato, definiamo dei contratti per i dati in input. Restringiamo quindi quelli che sono i dati che accettiamo. Creiamo quindi dei JSON schema dove diciamo questo campo non è un campo qualunque, è una stringa, deve essere lunga minimo 2 caratteri, massimo 30, magari ha un pattern che deve seguire, magari ha soltanto delle opzioni tra cui scegliere. Definiamo quindi un contratto che sia al contempo documentazione e formalizzazione di quello che vogliamo in input. In questo modo, nel momento in cui noi leggiamo i dati in input, la prima cosa che facciamo è validarli rispetto al contratto. Se i dati in input sono validi rispetto al contratto, allora passiamo alla parte di generazione che genera i file in output. Questo ci ha permesso di bloccare in anticipo tutti quei file di input non corretti che potevano o rompere il generatore, perché non era previsto avessimo quei dati in input, o peggio, non romperlo, ma causare la generazione di file in output sbagliati. Ora, i file in output venivano dati in pasto ad altre risorse e i file di output sbagliati potevano causare non pochi problemi. Ma come abbiamo rispettato i contratti che abbiamo scritto? La nostra idea all'inizio era di usare dei model pydantic. Dei model pydantic permettono la serializzazione e la deserializzazione dei dati. Il problema di usare dei model pydantic è che bisognava innanzitutto interpretare il JSON schema, che per quanto fosse scritto da noi è comunque un layer in più ed è un layer che può portare a creare un doppio standard. Nel momento in cui noi scriviamo nel JSON schema una cosa e dovesse capitare che la interpretiamo male e non la riportiamo correttamente nel codice pydantic, allora ci saranno dei dati che verranno accettati dal JSON schema ma non verranno accettati dal model e viceversa. Il secondo problema è che scrivere i modelli a mano vuol dire che ogni volta che il contratto viene modificato bisogna ricordarsi di scriverli, di modificarli, di aggiungere un campo. Modifichiamo un pattern, una regex, una virgola, bisogna ricordarsi di portarla anche nel model. Questo era un altro dei rischi di creare un doppio standard. Ci è venuto dunque in aiuto questa fantastica libreria che si chiama Data Model Code Generator. Dati degli input, dei contratti, possono essere OpenAPI che vengono usati spesso per le API, possono essere dei JSON schema, come ci sono stati utili nel nostro caso, possono essere tanti altri formati, genera automaticamente in output dei model pydantic. Possono essere, per chi fosse un po' più purista, delle data class in Python, dei typedict, o per chi fosse un po' più orientato alle performance, dei message spec. In questo caso a noi servivano dei model pydantic versione 2, erano supportati, li abbiamo usato per questo. Il vantaggio è che quindi, al netto di mezz'oretta per configurarlo, in pochi secondi, dati dai JSON schema, avevamo dei model pydantic sempre allineati, in modo quindi veloce, deterministico e abbastanza affidabile. Dico abbastanza perché purtroppo, facendo conversione tra un contratto e un'altra tecnologia, capitava che alcune validazioni non fossero totalmente corrette. Poteva capitare che, ad esempio, un pattern non fosse riportato nel model. Questo succedeva per i contratti più complessi, quindi vi invito, se volete usarlo, sempre a verificare il codice generato. Questa era la soluzione finale. Dati dai JSON file, si passava al layer di dati, in cui avevamo il contract validator che validava i dati in input usando i JSON schema, mantenendo quindi un'unica sorgente di verità, il JSON schema. Dopodiché, dati i JSON schema, avevamo generato i model pydantic e quindi deserializzavamo i dati con i model pydantic. Questo ci ha permesso di rendere molto più stabile e affidabile il nostro codice, che quindi ora accetta solo dati che ci aspettiamo di ricevere in input, e solo nel caso in cui i dati sono validi, allora passiamo al layer di generazione, dove abbiamo cercato di tener conto di tutti i dati in input che potevano arrivarci, che abbiamo deciso noi di accettare. Il layer di generazione a quel punto generava i file e li dava in output. Ricapitolando, i contratti ci permettono di definire delle specifiche del codice, di formalizzarlo. Nel design by contract noi definiamo i contratti all'interno del codice, con delle esterzioni, o volendo in Python ci sono anche delle librerie dedicate al design by contract. Nel contract first, noi, prima di qualunque implementazione, definiamo dei contratti, formalizziamo, quindi l'implementazione che abbiamo in mente, e ci accertiamo che sia ciò di cui si ha bisogno. Questo è utile, faccio anche un ulteriore esempio, nel caso in cui si vogliono creare delle interfacce, che siano software o meno. Nel momento in cui io devo creare un software che magari vuole supportare dei plugin, formalizzare, astrarre quella che può essere l'interfaccia tra il software e il plugin mi permette di comprendere meglio come devo scrivere l'interfaccia del plugin, lato core, e come devo scrivere i plugin, facendomi anche qui risparmiare tempo. Questo era tutto, questa è la mia mail se volete scrivermi qualcosa. Grazie.
Grazie, bella presentazione. Complimenti, bel lavoro.
Grazie.
Grazie a tutti per aver seguito Antonio. Se avete qualche domanda potete porgliela durante la conferenza.
Sì.
Grazie mille. Salve.
just a couple more minutes still. We've got 5 minutes, right?
Yes.
Awesome. So.
Sorry if I do you want some presentation or you're just okay. They say that you can turn on your microphone. They slow down the volume during the talk, and then they raise the volume when you start to talk.
So, okay, yeah, that's fine. And I'll just wait for that to.
If you want some water, I can. Okay.
Thanks, yeah.
Good morning, everybody. Hello. So, welcome to PyCon, Gnocchi Room. Now we have Andrew with his presentation. Just one thing. If you had some question for Andrew, please type the question on Slido. Do you know how to reach Slido? Okay. On link Python streaming, okay, under the streaming about Andrew, you can push the button ask question, okay? So please use this link, okay? So thank you, and Andrew, the floor is yours.
Thank you so much. So I know why all of you are here. You're here to listen to me make funny noises with my computer. But before I dive into anything audio related, I want to present a little bit of an analogy first. So let's say you are trying to model a traffic light signal, and you just want to emulate that signal turning yellow, then turning red, then it waits a bit, then it turns yellow and green again. Maybe you're, I don't know, a traffic engineer or something, and you want to be able to model the flow of traffic, and for that purposes, you need a simulated traffic light. So one approach that I might take, let's say I'm fresh out of school, and I think, oh, I know, I'll just create a variable for the traffic light state. So there I go, I'm feeling all clever. I create myself a lovely enum here with red, yellow, and green as separate states, and then I assign, for instance, the green state to a traffic light variable. And sure, this works, but it's not great because that traffic light is just going to stay green and green and green, and it's never going to change until you reassign it. And you could, for example, throw in a loop, add sleep statements, and you have a changing traffic light, but it's not great. You don't have a lot of control over that. And if you want to change anything at all, you have to change the entire way that this workflow works. So one way that you might do this instead is you might implement a signal workflow, where instead you would, for example, there we go. For instance, you could do something a little bit more complicated like this, where you decide to use a generator function. And for those that haven't used generators before, it's sort of like a regular function, except rather than returning a single value all at once, you can return as many values as you want forever by using the yield keyword, and it does that by using an iterator. So over here, for instance, this here is the generator function. It's taking in 3 parameters for the duration of a red, yellow, and green traffic light. And then afterwards, in a loop, it's just going to yield those values in turn. It's going to go red for however long you specify, then yellow, then green, then yellow again, and so on. And this is a better approach because now we've separated the logic. We've got one part where we define how the traffic light behaves, and another part where we actually are able to run this. So if I was to run this here, you can see that we now have control at the business end of things, at the simulation end. We can say, for instance, sleep 1 second in between each tick. And we have full control over that during the simulation. We can store the state of the traffic light. If we wanted to save the history of the past 10 seconds, for example, we can do that using just a list of length 10. And sure, this is cool and all, but what's the point of doing this? Well, this here allows us to use stream processing, where rather than waiting for some sort of computation to finish and you can do something afterwards, you have the ability now to do some sort of action right as the data is coming in. That sort of mock example of a traffic light could be a data source from absolutely anywhere. And what we can do with stream processing is react to real live world data, and this is used everywhere all the time. For example, finance firms absolutely love this because they get to look at stock market data and get to be the first to react to any price changes. This is used by meteorologists to predict the weather so that they can continually give you live updates about what they think will happen in the next hour, in the next day, in the next week, whether it will rain or not. It's used by roboticists, where they will be constantly reading live sensor data. For instance, let's say you're making a self-driving car. There will be dozens of sensors all over that car, and you need to react to things instantaneously. It's no use if the car's already crashed, and afterwards, in a post-mortem, you go, ah, yes, the car should have turned left over there. It's used by statisticians, because by processing data as it comes in, that can be much faster and much more time efficient than waiting until you have gigabytes or terabytes of data piled up. Then you run your Python script or a Jupyter notebook over that, and then you're stuck there waiting for hours, days, weeks, however long it takes to crunch through that. And lastly, audio engineers. Possibly indirectly, but this concept of stream processing is used all the time for processing all sorts of sound, for hooking up instruments. This microphone that I'm using now, it's all happening in real time. And sure, maybe the average audio engineer isn't thinking, ah, yes, I'm using stream processing as in plug this microphone in. But you use it for synthesizers, where you take some data about some parameters or what note you're pressing, and you turn that into an audio signal. It's used in effects. So, for instance, you might have a looping pedal, or you might have a reverb or delay or distortion effect used in a live band, which takes in some audio, mangles it or changes it in some way, and then outputs some more audio, which maybe sounds better or worse. Then you have audio interfaces, which is how you get computers to talk to instruments. So if I have an electric guitar and I want to record it, I can't just plug that guitar straight into a USB port. I need something in between which speaks the language of both the guitar and the computer. So that's constantly passing data and audio back and forth through it, and doing a lot of conversion, amplification to make sure that the levels of everything is okay, and all sorts of other clever tricks under the hood, which I am by far not experienced with, and the companies like to keep quite secret and stick fancy names on because it's what gets them to sell their products. And the list goes on. We're talking all sorts of instruments, microphones, mixers, recorders, speakers. All of them are handling this audio in real time. And this, at first, might not seem too difficult to do. Just write a program which has a loop in it, or waits for new data to come in. But if you take a peek under the hood, things do get a little bit more complicated than that. So let's talk about the headphone jack. Everyone's used a headphone jack. It's also known as the audio jack, phone connectors, aux ports. It's what you use to plug in headphones into your computer, or that port on the bottom of your phone, which everyone is now removing and charging you extra for a dongle. Headphone jacks are great. They're also probably the simplest connector to ever exist, excluding the power cable. And that is, they have pretty much zero latency. That is, the only latency is the speed that it takes the electricity to get through the cable. That's it. And they have absolutely no protocol. It's just raw voltage being sent right through the cable. Again, sort of. If you send 100 volts through a cable, you're probably going to end up breaking all of your equipment. But as long as you keep things under reasonable thresholds and you respect the voltage limits of whatever device you're using, any raw data you send in is just raw data that comes out. You don't have to deal with USB protocols. And it has an infinite resolution. Again, sort of. The resolution is just however fine-grained your measuring instruments are. What's being sent through is just a raw voltage signal. There's no set frequency for it. Just whatever value goes in is whatever value comes out. You can measure it using an oscilloscope from your school physics labs, for instance. And there is one massive disadvantage of using analog audio for everything, though, because by this point you might be thinking, if these are so great, why don't we use them for absolutely everything? That being that they can get a bit monstrous to use. This is an example of a modular synthesizer for making electronic music. And there are lots of hobbyists which love this kind of thing, but you're not going to fit this in your pocket. You're not going to be able to take this to your band gigs or wherever you want to take this. And it's really, really complicated to use, and will probably take the same amount of power as a family of 4 living in a suburb. So as an alternative, most of the music production we do now is digital. And going from analog to digital is actually surprisingly intricate. It takes a lot of maths, which is probably well above my knowledge grade to talk about, but we need to turn an analog signal, like we've got at the top, into a digital signal, which is shown in Audacity on the bottom there. We need a way to be able to read those values and get a computer to understand them, because computers don't deal well with infinite resolution or infinite data. So the way that we can go about this is we take that analog signal, which is sort of like an SVG. It's sort of like vector graphics in that you can just take a bunch of samples of that and slice it up into a bunch of small pieces and then store the values at each piece. So on that bottom graphic there, you might be able to see a bunch of dots there. Those dots are individual discrete samples of a wave. So in order to convert that, we now have to ask ourselves the question, how rapidly do we want to take those samples? if we were to convert from a vector image to a bitmap image, that's going to have a resolution. So what's the equivalent for audio? Well, we have what's called sample rate, where we ask ourselves, for each second of audio, how many pieces do we want to slice that into, and how many samples will we then be storing? And the higher the sample rate, the higher the resolution. So as you can see here, if we were to take just this simple sine wave, if you sample 10 points, you get a pretty good representation of the sine wave. If you only sample 2 points, you can barely tell what's going on. You have no way of telling whether that was originally a sine wave, or a sawtooth wave, or something else. So the trade-off there is just the more data points you sample, the bigger the file size, the more it takes to process, but the finer the quality, the more information you store. And the less you sample, the less information you store. Except there's a bit of a catch in that some very, very clever people went and developed something called the Nyquist-Shannon theorem, which says that if you have twice as many sample points as the highest frequency in a wave, you are able to reconstruct that original wave perfectly. Which is a bit of an odd concept to think about at first, because that's like saying you take a vector graphic, you turn it into pixels, and then you can turn those pixels losslessly back into the original SVG file, which isn't normally possible with images, but it is with audio. You can do all sorts of maths involving Fourier transforms to reconstruct the original wave, and you know exactly what you had previously. And since the upper limit of human hearing is roughly 20 kilohertz, so 20,000 samples per second, double that would be 40 kilohertz. So the standard sample rate for most audio that you listen to is just a bit above that, just as a little insurance. The standard is 44.1 kilohertz, which means that when you play audio through a computer, it is moving the speaker position roughly 44,100 times a second, which is a lot compared to other media formats. For instance, this projector here is displaying at 60 hertz. It's updating the screen 60 times a second. My display on my laptop is 165, which is 165 updates per second. 44.1 kilohertz is still going to be 2 orders of magnitude higher than that. And computers don't really like that. Oh, look, I've got a lovely to-do message there. Isn't that wonderful? Must have pulled the wrong version of the presentation. Oh, well, happens. So the solution to this is buffer size, because computers don't really like it when you tell the computer to run something 44,100 times a second. Python will manage it fine, except the moment you decide to do something else on your computer, say you launch an app, that will cause a tiny bit of latency. And even if that causes just 1 millisecond of latency, even if it updates 1 millisecond late, you'll hear that as a really ugly pop on your computer. And your music will be all nasty and distorted. So the solution is something called buffering, where rather than saying, OK, play each sample one by one, move the speaker one position at a time, we allocate it into chunks. So for instance, we can have a sample size of 128, which means that we are going to have a list of length 128, and then we are going to render out all 128 samples, decide where the speaker has to go for them, and then give all of that to the speaker all at once. The speaker then has a digital audio converter, which takes that information, parses through it, figures out where to move the speaker, and then all's good. You get to hear your music without any ugly distortion. However, it does mean that we have a little bit more work to do on the programming side of things. So to present an example of that, let's say we want to make a sine wave. Finally, I'm tying this back to the software in question. This is about synchrotron, which is a program that allows you to construct your own synthesizers and process audio just by writing Python. And I'm going to create a sine node, a node just being a single module which takes in some data in and puts some data out. You can think of it as being equivalent to a single instrument or being a single effects pedal. So what I'm going to do is I'm going to define an input and an output. I've got frequency in, and I've got an output that's just named out. Because if you want to produce a sine wave, you need to know the frequency of that sine wave. You need to know how fast it's going to oscillate. And then afterwards, you want to be able to actually send that sine wave somewhere, for instance, a speaker, so you can hear it. And I'm going to create this render function here, which takes in some rendering context. This has information such as how big do we want this buffer to actually be? Do we want a 128 buffer, which would be quite small and you'd have almost no latency, or do you want a massive buffer? Let's say we had a buffer of 44,100 length. In that case, the buffer would be an entire second. So all playback would be delayed by 1 second. However, it does mean that if the computer's a bit slow, it has that leniency of 1 second to catch up. So as long as it gets the audio done within 1 second, you're all good. And firstly, I'm just going to use NumPy. I'm going to create an empty array with the length of the buffer size. And I'm going to use floating point values between -1 and 1. And I'm going to write this to that stream output. And this, so far, isn't very interesting. It's just going to produce complete silence. It's an empty array. It's writing an empty array to the output. You're not going to hear anything. So let's now actually produce that sine wave. So I'm going to add a constructor. This is just standard Python stuff. The node takes 2 parameters. One of them is this synchrotron parameter, which is a global object that holds the state of the entire program, and the other being the name of the node, since each node needs a unique ID for the program to keep track of. Those are just being passed into the constructor, which isn't particularly interesting, but we are going to create this field here. We're going to say, let's create a phase variable and set it to just be 0 at first. So then what we can do is inside of this render function, we can say it's time to actually produce a signal. We're going to read in the frequency from that input. So for instance, that could be 10 hertz, so the speaker will oscillate 10 times a second, or it could be 440 hertz, the speaker will oscillate 440 times a second. And we're going to say, for each sample within that buffer, we are going to take the sine of the phase and write it to that buffer. So we're computing just this buffer at the moment. This isn't being written directly to the speaker, because that's where you get all sorts of nasty, garbled audio. All we're doing is we're going to compute the sine of this one sample, and then we're going to increment the phase. So we're increasing the phase by 2 pi, multiplied by the input frequency and divided by the sample rate. So this is just saying, if you were to imagine an angle that was revolving within a circle, 2 pi would be a full revolution. Therefore, 1 hertz would need a full revolution. If you increase the frequency, you want to revolve more times. And if you have a higher sample rate, you have a smaller jump between each sample. Therefore, you need to slice it up into smaller parts. And altogether, this will create a sine wave that will be output to that stream output. But let's see that in action now. So this here is synchrotron now running. And I am going to use this console over here to say, let's create that sine node that we just demonstrated there. And here it is. But by itself, it's not actually doing anything. It needs an input and an output. So I'm going to say, let's input a value of 440, and let's output to a playback node, which is going to run it through the speaker. So if I was to take that 440, wire it into the sine node, then take that sine node and wire it into playback, you get a sine wave, which is nice, cool, but it's not that exciting. We can do more with this. That input there, that 440, isn't just a static 440. That is still a stream. So that is the value 440 being passed into the sine node 44,100 times a second. It doesn't have to be static. We can make that, for instance, the output of another sine node. And what we would want here is, right, let's see, there we go. what we could say is make this sine node oscillate. Currently, it's going between -1 and 1. Let's make it go between -440 and 440. So to do that, we need to multiply the amplitude of it by 440. And that sine node there can have a frequency of, for instance, 1. So now, lots of dragging and dropping. But I should be able to take that sine node here, multiply it by 440, and then make that the new frequency. And now you can hear it oscillate. It goes woo, 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 and gets very annoying very quickly. But this is a simple and very annoying example of something called frequency modulation. This is the same thing that, for instance, your FM radio does in order to communicate all sorts of information wirelessly over radio. It's also used very frequently in music and sound design. But this can be built up potentially limitlessly. Your only limit being how fast your computer can actually run this. Eventually, you'll have such a big graph that it'll be too slow to actually compute. It will not finish rendering those 128 samples in time, and then you'll hear a tiny bit of silence every 128 samples, which you'll hear as distortion, which sounds absolutely nasty. You might have heard it before if your computer's lagging, and then all the audio goes all glitchy. So the only limitation is now just how much compute power you have. And this system doesn't have to only deal with static values that are created in the computer. You can also take in data from externally. For instance, I've got myself a MIDI keyboard over here. And if I was to, hopefully, what I should be able to do is create a oh, let's see, where is, sorry? Oh, right, thank you. There we go. So then new sine node, new playback node. What I'm doing here is I am saying, let's read whatever that keyboard is transmitting on port 1, and then turn that MIDI information into a frequency, which is what this monophonic render node here is doing. After that, take that frequency, pipe it into that sine node that we made earlier, and then play it out to the left and right speaker channels. And hopefully, there we go. Now you can use this as an instrument. And this is exactly what is happening when you play a synthesizer or play a keyboard into a digital audio workstation for music production. For instance, FL Studio, Bitwig, LMMS, there's loads of them, and different music producers tend to get into fights over which one's better, just like with Linux distros. But that there is how, in a pretty simplified form, but that is how synthesizers and audio processing on a computer works. Normally, this would be implemented using frameworks like the Juice framework, which is C++. As far as I'm aware, I think this might be the first time this has been done entirely in Python, unless you count the NumPy stuff, but you can also just use Python lists if you wanted to. And this can be not as scalable as implementing this in a compiled faster language, but one advantage of doing this in Python the language we all know and love, is that you can do a lot of stuff with dynamically loading in modules. So I don't have to restart the server if I was to program in a new node, for instance. This opens up a lot for live coding and for interactive development. You don't have to rebuild and recompile everything. You don't even have to restart the server. You can do some really cursed things using importlib. And there you have it. That is synchrotron. You are more than welcome to try it out for yourself. I will warn you, the documentation is currently incredibly limited, but if you do reach out, genuinely, I'm always happy to answer questions or help out in whatever way, shape, or form. Thank you so much.
Absolutely fantastic. Good work. Well, you have a question, okay? What will be the impact of having stable quantum computers for analog signal synthesis?
Sorry, could you repeat that, please?
Yes, yes. What will be the impact of having stable quantum computers for analog signal synthesis?
As far as I'm aware, absolutely nothing, because this is most likely a task better suited for classical computing. Even if we did have stable and fast quantum computers, there is no computational benefit, as far as I'm aware, to actually running any sort of digital audio processing through quantum computing. That's mostly, as far as I'm aware at least, useful for sort of statistical purposes and improving, time complexity with things like cracking passwords and whatnot. But I am just saying words. That is well outside my domain of expertise.
Okay, perfect. Let's see another question. Can you use synchrotron out of the box without writing Python code?
Yes. So it does come with a bunch of built-in nodes. All of the nodes that I used currently are all built in. You can expand it just by writing your own code right into a directory called nodes. And then as long as Python is able to see them, you can expand as much as you want.
Perfect, perfect. Well, another one for you. Can you share the name of that cute little MIDI keyboard?
Yes, of course. This here is the Teenage Engineering OP1 Field. It is meant to be a standalone instrument as well. I'm using this as a MIDI keyboard because it is the most portable MIDI keyboard that I own. It's also the only MIDI keyboard that I own. But yes, it's an OP1 synthesizer.
Thank you. Well, there's another question from the audience.
Thank you. I'm an hobby synthesizer playing too, and I just want to make you congratulations for this, because for your age, it's really amazing, and just congratulations for you.
Thank you so much.
Very, very good work.
Thank you.
Not really a question.
I share a similar sentiment. I've built an audio library myself called Easy Audio.
Yes, I've seen Easy Audio, yeah.
Yeah. So very impressive to see it in Python, because like I come from the world of like C, C++, like the juice kind of audio processing things. So one thing I had a question about, just because like clock time synchronization between nodes, I saw that you had like a global object that you're using there.
Yes.
Is that sort of encapsulate? Let's say I have like in this case we had sort of like single sort of node going into like multiple effects chaining, but if I had like a file player and like I had like 3 nodes, like a multi-track kind of thing, how does synchrotron deal with that?
So synchrotron does actually have a node for reading in a WAV file as an input source, and the way that this is handled is that each of these output nodes, these playback nodes, register themselves globally as being a target audio sync. And then the bottleneck just ends up being whichever is the slowest output sync. So for instance, if I have just this here, the bottleneck would be the audio driver, where the audio driver has a callback where it's after it's played a buffer, it's going to say, I need the next buffer. So it's going to be more or less real time. If I replace this with writing to a WAV file, it will run as fast as it can, as if you're rendering or exporting audio from a digital audio workstation. If you have both, then it will write the WAV file still, but it will only write it as fast as the playback node throttles that.
Interesting. So you could have like an offline rendering sort of node
Yes.
as well.
And if I if I use the console here, there is a global clock which keeps track of the current time in number of samples, which is how it keeps everything in sync.
Gotcha. Cool. Great work. Yeah.
Thank you.
Thank you, Andrew.
Thank you so much.
Congratulations. So. Thank you, everybody. So we finished for this morning. Have a good lunch.
Okay, I think we can start. Welcome everybody, and welcome to our first speaker of the afternoon, Alessandro Cosentino, who is going to talk about the use of Python for quantum computing. Remember, if you have any questions, write them down on Slido, and I will ask them to the speaker after the talk. If we have time, we can take live questions. So welcome, Alessandro. The floor is yours. And
thanks, Nicole. Okay, so last year, in our organization, we ran a survey, a quantum open source survey, and we asked basically all the quantum practitioners what language. We asked many questions. The 31st question was like, what language do you use to develop quantum software? And as you can see, 95% of people replied it's Python. And yeah, you can see the full stats on the website there. And we have been running this survey for like 4 or 5 years, so we also track trends. And you can see there is some interesting trend if we compare with 2022, which is Python is still up there, 90, in fact, is increasing by 1%. But what's emerging is languages like Rust, which 2022 was used by 7% of practitioners, and now it's used by like 13%. So, and in fact, the next question was, which language would you like to learn? And it's most promising for future use, again, in the context of developing quantum software. And the answer for the first year was that Python was not the first one, but Rust overcome Python. And that's, you know, for a Python audience, something to be worried about. So the topic of this talk is like, can we do something to sort of invert this trend and keep doing quantum software without leaving Python behind? And that's also a selfish goal, because I don't want to learn another language. I want to focus on like my quantum research stuff. I'm sure Rust is great. I was at Luca Palmieri's workshop this morning. But I still want to keep focusing on, you know, my quantum stuff and do things in Python. So let's see if that's possible in the future. So to set up the scene of this talk, I'm going to give an introduction to quantum computing in, I promise, in 2 slides. You don't need to know any quantum physics. I don't know any quantum physics myself, even though I've been in the field for a long time. I'll go through the quantum software stack. I'll explain the role of Python in the current stack. Why do we need speed for classical computer in the quantum stack? And I will use 3 case studies. A simulator, you will understand what that is, a transpiler, and a compilation engine, where this trend is visible. So they are sort of shifting to more like native and performance languages, sort of leaving Python behind. So quantum computing in 2 slides, it's ambitious, but I will try. So quantum computing is a paradigm that uses properties of quantum mechanics. Superposition, entanglement, and interference are the most important to improve what we can do in terms of speed and security with computers. It's been an area of research for 20 years. I've been involved in that for like maybe 10 years. And hopefully, feasibility is coming in 20 years. It's obviously hard to predict. I just put it there because usually it's one of the frequently asked questions. So where are we now? We are in something that people call the NISQ area. So we are at intermediate scale, so around 100 to 1,000 qubits that we can engineer and they can perform. But they are still noisy qubits, so we cannot really do many things with them. It's still an incredibly interesting area in terms of research, and we do want to scale to not having noise and many more qubits. So the application, obviously, the most famous is that if we actually implement quantum computer, we can break RSA. So we can break some protocol of cryptography as we use them now. But what is probably more interesting, because it needs less scale, is that we can simulate a quantum system, which is something that would take lots of time and lots of processing, time and energy to do it with classical computer. And simulating quantum system is really useful because if we have that, we can do things like more efficient fertilizer, which is good for agriculture, I guess, or new drugs, like pharmaceutical drugs, and like new materials and things like that. So things that are extremely important. I don't understand many of these applications, but even from the title, you can understand they are very important. And we can do, in a slightly more efficient way, also things that we already do with classical computer, like routing and scheduling. So more from an algorithmic point of view, what we want is to have a quantum computer. That's sort of the end goal, is to have a quantum computer that can solve a problem that we care about. So it's not like a made-up problem just for research. Perhaps one of the problems I was talking about earlier, that we can solve faster, or if you prefer some other metrics, cheaper than with a classical counterpart. So, and from the algorithmic point of view, we made great progress in the last 20 years. We have an algorithm that can do unstructured search, so you have n items and you need to look for one. The best we can do classical is like linear, but we can do square root of n in the case of quantum algorithms. We can do factoring, which is at the base of the RSA protocol and cryptographic protocol I was speaking about, where the best classical is sub-exponential on the logarithmic of the number you want to factor. So just maybe you can look at it as the logarithmic is like the number of digits of the number, and the best algorithm is sub-exponential in terms of that. But it turns out in quantum, because of Shor's algorithm, probably the most famous quantum algorithm, we can do this in polynomial time in the number of digits of the number. And that was the biggest breakthrough for quantum algorithm research. To simulate quantum physics, here the equations are more complicated, but again, the improvements is sort of exponential. So what you can simulate now, a system, a physics system that you can simulate in exponential time, you will be able to simulate it in quantum polynomial time. So that's all nice, but it obviously assumes you do have a quantum computer, which at the moment is not yet the case at a large scale. But anyway, hopefully you were already somehow familiar with quantum computer, and this just gave you a recap. In fact, the news of this week is that the threshold for the number of qubits that we need to break RSA was improved to be less than 1 million. The paper is still under review, but that's, as I said before, we are around 100, 1,000. 1 million sounds very far away, but in my opinion, achievable. We will save the question for later on, like, what happens if we break RSA, because that's not much the topic of the talk. So that's all nice from a research and algorithmic point of view, but if you are just like a software engineer and developer, you probably don't really understand what you can do right now with quantum software. So I'm going to go through a typical workflow of a quantum computer developer. So first of all, you either develop an algorithm or you speak with a friend who is an algorithmist in your research group. And what they will do is come up with something that looks like this. So it's basically, if in classical computer science you studied like Boolean circuits, this is sort of similar, But instead of like AND OR gates, you have some different kind of gates. And instead of like bits on the left as input, you have qubits. And then at the very end, you have this concept of measurement, which is basically observing the states. But the point is that this is really something that you do on like pen and paper. You like solve some equation, you prove a theorem. If you are sure these circuits will help you break quantum cryptography, but otherwise it will just stay in a paper. So next, you can actually code this up. So if you have a circuit like this that you find in a paper, you can actually install something like Qiskit, which is a library in Python by IBM. And you can define things in Python, the same things that are drawn there in the circuit. So you can say, OK, I have 10 qubits. I want to build a circuit which has 10 qubits. For each circuit, I want to apply this gate on the qubit I, which is sort of what we are doing here, assuming these were like 10 qubits. Then you do other things here. You apply some gates, and then you measure them all. So there is sort of an API to do whatever you do on paper to define circuits. And once you define the circuits, you really define a quantum program. So you have this Python software. So this is the Qiskit symbol right here. And let's say now you want to run on an Amazon bracket device. So it turns out that AWS also has quantum computer that you can access on the cloud, and you can dispatch jobs that are written in Qiskit in this Python toolkit. So what you do, you pip install some library that is called Qiskit bracket something, and then you import this, and then you instantiate the backend, which in this case, you notice it's local, which means it's just really running on your machine, but it's a simulation of what would happen on the quantum computer, and you run it. And this is really to simulate that you are doing the right thing. Obviously, as we were saying before, this will take lots of time on your laptop, especially when the number of qubits increases. So it's really just to proof check that you are doing the right thing on small inputs. Next step, as a quantum developer, you say, OK, this is running fine on my laptop. Let me try on another simulator, but this time on the cloud. So it turns out that Amazon are actually some like machines that are classical machines, but that can simulate exactly what a quantum stack would do. The machine is called DM1. And you can actually instantiate that. You can, same story. You get the backend. You run the circuits. You get some result back. And you say, OK, this is running fine on the classical simulator on the cloud as well. So now you really are confident enough that you can spend money on the quantum hardware, which unfortunately right now is still quite expensive. So every time you run a job, it will cost you much more than, let's say, an EC2 instance on AWS. But now you're confident because you trusted your algorithmic friend, you are good at writing Python, you simulated on small input, you simulated the cloud, the jobs are dispatched to the cloud perfectly. So now you can run it to an actual hardware. And this is from the point of view of sort of the user developer that just want to run things on a machine. But in this talk, we are going to see what happens actually behind the scene when something is run on a hardware, or rather on a cloud computer stack, which can be Amazon bracket, it can be a Google stack, it can be an IBM stack, and every company that owns a quantum computer. So this is the stack. So something important to notice here is that as opposed to classical computer, where most of us, I guess, we were born when most of the stack was already there. So we just went to uni and we learned Python. We maybe learned some assembly, at least I did in undergrad. but we didn't learn things like, at least I didn't learn things like error correction and how to do it in like, how to manipulate bits so that they are encoded and they are, you know, that the computer runs without error. You never cared about things like that. It turns out in quantum, we are at the stage where we need to care about those things. And it's actually, in my opinion, really interesting and really exciting because we have the opportunity to learn from classical computer and like reformulate completely the stack from the ground. So what you see here is a real picture of a machine of IBM. The quantum chip is somewhere here. I don't really know. As I said, I don't understand engineering, like mechanical, electrical, or physics. But as far as I understand, all of this is a fridge to bring things down to very low temperature because that's how superconducting works well. So let's say we don't care about this stuff here because we are mostly computer scientists. But right on top of that, we need to write some firmware. And some firmware that will allow us to go from what we wrote in Python to things that are closer to machine level, which are things like pulses. So you actually have like laser pointing at superconducting material things. And that will simulate whatever you want to do on a qubit. So let's say you want to apply a NOT gate. When you have like a 0 qubit and you want to flip it, that's called the NOT gate. So you do that by actually shooting some laser against something. So it's a very physical thing. They are called pulses. And you need a firmware to control these. And the firmware is actually classical. So the nature of the thing that will happen after you shoot the laser against the material is quantum. But the way you control these pulses are classical. So this is the bottom of the firmware. But let's go back to the top, which is the algorithm that our friend provided. So let's say we start from there. This is exactly, I think, the same circuits as before. So we did write it in Qiskit. So now it's in Python. We don't need to, parse a PDF with a picture here. So we have it in Python. And now we can compile it back. So compiling in quantum is a bit an overloaded term because it means both going from a high-level language to the low-level language of pulses, but it also means something else. Like we will see it later in one of the case studies that not all the devices support all the gates that you can specify logically, so you will have to do some optimization there. And as I say, there is a full stack of like controlling the errors so that you can reduce the noise of the computer. So what is important is that all of this stack is really classical software that runs with like classical languages like Python. And only at the very end you have physics and like quantum mechanics that acts upon the qubits. And in fact, in the example we were saying before of development workflow, what you want to do is simulate even the physics part. So often you want to build a classical simulator because you want to be confident that what you will be doing, the money you will be spending on a quantum hardware is actually worth. So what is the role of Python in this stack? So it actually has a big role currently, as you said. In the survey, 95% of people are still using Python. And that's because we have many domain-specific language or embedded domain-specific languages that are written in Python, and thanks to which you can write quantum algorithms. Things like, this is probably the things you have heard of, is Google Circ is an example, IBM Qiskit, which we used for our code snippet before. There are other smaller companies like Rigetti's, PyQuil is one of them, and so on. So defining a quantum program is something you can already do in Python. The choice of Python is because we already have libraries. This is mostly a research field. There is lots of hype, in newspaper and things, forcing it not to be a research field, but effectively it's still a research field. So most of the people working on it are still scientists, are people like mathematicians, physicists, and these people mostly like Python. So they have access to lots of tooling, lots of libraries like NumPy, SciPy, Matplotlib, and all of these are in Python, so we want to reuse those. So at the level of front end, we are sort of set on Python already. We do want to do rapid prototyping of these algorithms. So we use things like Jupyter Notebook, same as like you want to do a rapid prototyping or like of data science or machine learning stuff. And in fact, we are using the same proven pattern that we already use in machine learning. So we have a Python front end. But what is emerging now is that things that are below the front end in the stack are written in like more performant languages like C++, or they use libraries like NVIDIA, CUDA, for efficiency mostly. And something that is also very important is that we are at the research level, but we are also at the point where we are learning and teaching quantum a lot more than actually solving practical things with. And this is really important to, raise a generation, assuming there will be another generation of people that people will work on quantum and hopefully build a quantum computer. So yeah, and education, as you know better than me, probably Python has been so far the most successful language for that. So, and the next question is like, why do we need speed in this stack? So that's because when you are prototyping, you do need very quick feedback. You want to type an algorithm. Again, this is the same in classical or quantum. You want the results to come back to you in a very short time. What is also interesting is that we are writing algorithms that are sort of like a ping pong between QPU, which is the quantum processing unit, and CPU. So there are so-called hybrid algorithms where some computation happens on actual classical clusters or high-performance computers, and then you send the results to the quantum machine, and then the results comes back. You do some post-processing. You send back the input, and so on. And this is really important in things like error mitigation, which is one of these components I was showing before. I was showing before that allow to correct the noise on the machine. Something to keep in mind is that the scale here, once you want to simulate a quantum algorithm into a classical computer, the scale goes again exponential. So you can take a qubit and in a very naive way map it to a vector, something that we will see later. But if you keep doing this for 50 qubits, you will already have something that is like 16 petabytes of data. So at that point, if we want to simulate things before running on a machine, we need high efficient classical software to do that. And finally, at the very end of the stack, we need to control this physics phenomena that happen with certain clock. And we want to catch up with this clock in an efficient way. So the firmware that controls these pulses I was showing to you before, the firmware needs to be as efficient and with the same clock as the phenomenon that happened there. So you want something that performs really well and fast. So because of this need for speed, it turns out that many people are keeping Python for the front end, but they are dropping it for things that are so-called the hot loops, where you need more performance. Things like simulation, like transpiling, like the firmware control. And I'm going to show you 3 case studies where this happens. I picked these 3 case studies because my work has intersected into those in the last year. So the first case study is something called CRACK. It's developed by ourselves, the Unitary Foundation, and it's a quantum circuit simulator. So you can run it on your laptop, and it's open source, and you can, as input, take Qiskit circuits, the same one that you dispatch to quantum hardware, but you can actually simulate with and without noise on your computer. And the way you can imagine simulation in quantum is you take 1 qubit, and you can express it in the form of, if you know a bit of linear algebra, this is just like a vector. Let's say the qubit 0, you can express it as a vector of 1 and 0. The qubit 1, you express it as a vector of 0 and 1. And the superposition of qubit 0 and qubit 1, you can express it as like alpha and beta in a vector. And any transformation, like the NOT gate I was talking before, the one that flips a qubit, you can express it as a matrix. So you can understand that once you scale this to multiple qubits, from 1 qubits, now you have 2 complex numbers. In this case, they are integers, but in general, they are complex numbers if you have like alpha and beta. Let's say you have 2 qubits now, then you take the tensor product of these and another qubit, so the size of this vector becomes 4. And then it becomes 8 and so on. It scales exponential. So what you will have to run on your classical machine is basically matrix vector multiplication with huge matrices and huge vectors. And in fact, if you have a number of gates in the circuits, so the squares that you were seeing in this picture before is G, and the number of qubits is N. The runtime is of the algorithm, the naive algorithm to simulate is something like G times 2 to the N. And there is not much we can do better than this, obviously, because otherwise we wouldn't need a quantum computer at all. So they are basically classical linear algebra tasks that we sort of already learned how to do with GPUs, because we are using them in like machine learning already, and like video games or like 3D graphics. So fortunately, we know how to do them faster, not incredibly fast, but we know how to do them more in parallel. So the requirement is something similar what GPU is good for. There are other simulation techniques that are more complex, but as I said, they are not extremely more efficient than that. And in particular, one of the requirements of our simulator is that we want it to be used for things like education, or to be used even on your browser. We have some like web assembly way of running it. So we are really stressing on portability so that many people can use it. So that's another requirement. And we want to accept circuits written in any of these front-end languages that I was talking before. So let it be Qiskit, Circ, or like Penny Lane. We accept all of those. So the way we are doing it is we wrote core in C++ 11. This is mostly work by my colleague Dan Strano. And it's basically an external dependency-free package when it comes to CPU. And if you want to use GPU to accelerate the simulation, you can use the OpenCL libraries. And then we just have a wrapper around it, binded with C-type to C++. And that allows us to use Python as a user of the simulator, but all the speed and the need for speed I was talking about before happens in C++. So this is an example of performance. You have like 17 seconds to run at 27 qubits. This is one of the algorithms that is used for cryptography. And this is where you can run it. It doesn't scale much more than that. You can wait for maybe 1 hour to have like something like 30, 35 qubits, but then it becomes very, very intensive. But still, thanks to C++ or the performance with C++, we can get some very good number for a good number of qubits, pretty similar to the number of qubits that we would have on quantum hardware anyway. So another case study is a transpiler by IBM. It's part of the Qiskit toolkit. And what is a transpiler in general? So the problem it solves is like, we have these circuits, we have these algorithms, and now we want to run them on hardware, quantum hardware. It turns out that the physical devices, because of engineering limitation, have lots of constraints. So the gate set is not the same that you don't have the same freedom that you have in when you write the circuits on pen and paper or in like matrices. Because of engineering limitation, they only implement certain gates. So that's limited. The connectivity is limited. So this is a real example of connectivity graph of IBM Q Yorktown. I think is a decommissioned machine. It used to have 5 qubits, but for example, qubit 0 and qubit 4, or qubit 1 and qubit 3 were not connected directly. So you couldn't put a gate directly there. And in general, maybe one takeaway is that hardware is really noisy in quantum. So let's say you have a logical circuits like that, where you use X gate, use H gate. Again, you don't really need to know what they are, just think they are like AND or NOT gates. But you do understand that there needs to be between 1 qubits and one other. And for example, if the algorithm was written like this, there would be a connection between qubit 1 and qubit 3, but the connection in the hardware doesn't exist. So the first thing you want to do is transpile these circuits to a circuit that, first of all, matches with the gate set of the hardware, but also with the topology of the hardware. So you don't have any more connection between 1 and 3, but you have only connection between 0 and 1, for which we have an edge for between 1 and 2, and so on. So you can see the size of the circuits is slightly larger now. The gates are different, but logically, the circuits is doing the same thing. So if you calculate the metrics that correspond to the circuits, and you calculate this one, they are exactly the same thing. So in fact, this is not even a problem with metrics. You can see it as a problem with graph. So given a graph like that with some nodes and some edges, can I map a graph to this topology? So this is a classical problem that has application in quantum computing, and that we want to solve really fast because these circuits really, we don't want them to blow up, and we want to solve them really efficiently in a way that the output circuits is as efficient as the one that was written logically, otherwise we lose the computational gain that we gained in terms of algorithmic time. So this is a case study where the problem is really, classical, and the IBM team was struggling to get good performance with Python, so about in 2022, so 3 years ago, they decided to rewrite the package that does transpilation in Rust. And that's because of the thing Rust is famous for. You can do things in parallel in a safer way, and yet you have the portability and the platform support that maybe you don't have as easily in C or C++. So another advantage of Rust is that you can still package it in Python, so you can still reuse the Qiskit ecosystem. And the way they achieved it is actually through these PyO3 bindings that Luca was talking about this morning. So what they achieved, you can see all the results in this repository, where they also have a framework to benchmark these transpilation tasks. By going between version 1.2 and version 1.3, the API didn't change of this transpilation. The feature didn't change. Well, maybe some feature did change because they did upgrade the major version, but the minor version. But what they achieved is actually 6 times speed up on something like on average on the transpilation task on a single GPU machine running with Python 3.10. This was 3 years ago. And in fact, since then, they improved it even more, so they have now a 20% speed up on top of that. So the last case studies is a compilation engine. So as I was saying before, compilation is a bit of an overloaded word in quantum. You need to take an abstract language and bring it down to the level of pulses, but in the middle you also need to do this program optimization, this has error mitigation, error control. So that's what a compilation engine does. And this team from Canada, Xanadu, decided to write a just-in-time compilation engine for programs that they already have in this language called PennyLane, which is basically one of these embedded DSL that are written in Python. So it's still something that you can use in Python by just decorating your circuits. The circuits is just a function for them. And then you can decorate the circuits with @QJIT, so quantum just-in-time. And just by doing that, behind the scene, it will be compiled in a just-in-time way, and you will have more efficient performance. These are some of the gains we tested ourselves. This was something I was building for them, some error mitigation stack, and we experienced that on a small toy example of 3 qubits, we have like 3 times the speed that without exactly the same code, but without decorating the circuits with just-in-time. So the stack here is more complicated, but so it goes through MLIR, if you are familiar with that, but the essence here is the same. You have a Python front end. You want to lower it down so that the core and the part where you need speed are written in something more performance than Python, which is C++. So, and in this case, the tracing is done by JAX. This is like more technical thing that you can look it up, but some binding to get back the function are in nanobind, which is sort of like PyBind 11, but slightly more efficient apparently. But yeah, the point is that the front end is still in Python, so you can write circuits in Python. Everything that happens behind the scenes, so sort of like the cool, interesting parts is in C++. So I'll skip the bonus slides because running a bit time. So what is the moral here? So I just showed you three case studies because I skipped the bonus one. One was a simulator, one is a transpiler, and one is a compilation engine, where that they are solving tasks that are really important for quantum software, but they are not quantum physics tasks. They are just classical tasks that we can solve with classical computational languages. So we used to solve them in Python in the beginning when we were writing prototype in this field. But now we are at the point where we need the speed in most of these tasks. So we are resourcing to languages that are more performant. So C++ is one of them. Rust is becoming one of them. And we want to keep the front end in Python for the reason I was saying before, for education, for rapid prototyping. And we just bind things with between the performance language and Python with either C-type, PyO3, JAX, and nanobind. So this is at least the trend I observed, and I wanted to share this with you because maybe there is something we can do about it. Maybe the part that is really interesting, in my opinion, in quantum is this part where you need speed and performance. And I don't want to learn C++, I don't want to learn Rust. Can we stick to Python for these things? Going back to the survey, can we make sure that Python next year is again above Rust? Can we bring back, in other words, is like, can we bring back the quantum hot loops back to Python? So there are, in my opinion, some promising paths. This is mostly like an open question. It's something that I'm asking myself. I'm going to share it here. I'm doing some benchmarking and some prototyping. So maybe there is some hope. There is, the thing that we just saw, the compilation engine was using just-in-time, which is something that was introduced in just-in-time compilation, which is something that was introduced in Python 3.13. So maybe we can use the same techniques or use the very same compiler to do some of the quantum software compilation. We can do maybe better multi-threading, better parallel tasks, which are tasks like the one I showed you on transpilation on the graphs, or tasks like the simulation one where you needed the help of a GPU, of a GPU. Maybe we can start doing them in Python if Python becomes more efficient. I know there is an optional way to disable the GIL in Python 3.13. So maybe that's something to experiment with also for quantum tasks. CUDA by NVIDIA now has a native Python support since April 2025. There is a new language, Mojo, written by the same person who developed the MLIR stack, that promised to have some of the feature of Rust, but with the same syntax as Python. So maybe we can write a quantum computer simulator in Mojo, for example. So in my opinion, there are things we can do here. Yeah, that basically. Oh yeah, some notice that some of these things are experimental. I think the JIT is still like, there is still not much improvements, but in terms of benchmarks, but there is a bit of speed improvements. It's still in experimental mode. I think disabling the GIL is not really recommended, it's optional, but you can do it since Python 3.13. So yeah, I encourage people to experiment with those things when it comes to quantum computing tasks. That was the end of my talk, but I just want to plug two small things. So we are running a hackathon where you can actually get real money. You can go on unitaryhack.dev. There are 50 open source projects with bounties attached to it. You go there, solve them. Most of them are classical problems like the one I was talking about before. There are 800 hackers that signed up, and yeah, you can win things like $100 to solve a GitHub issue. There is also a real an event in real life in Milan on June 9. And also we are hiring a full stack web developer. Yeah, reach out to me if you're interested. Yeah, that was everything.
Thank you so much. That was great. I see just one question on slide so far. It asked whether QREC support Apple Silicon CPUs.
Whether, sorry?
QREC supports Apple Silicon CPUs.
I believe so, yeah. Yeah, I think you can run. Yeah, I'm pretty sure you can run things. I don't know how much it exploits the power of like M1 chips or M chips, but it does work there, yeah.
I don't think we really have time. If there is one question maybe from the audience, you can take it. Is it working? Yeah.
Thank you.
Thank you so much.
Yes.
But I didn't want to ask on the mic.
Oh, okay, yeah, that's fine.
Out of interest, why not PyCon? Or
È romanesco. 10 qubit, 2B.
Cominciamo, benvenuti a tutti, questa è la seconda talk del pomeriggio, se rimaniamo sul quantum, e quindi benvenuta la nostra presentatrice, Yuna o Giuna, apparentemente possiamo accettare entrambe le versioni, e ricordo a tutti di fare domande su slide che porrò alla speaker alla fine della talk, se rimane tempo facciamo domande live. Buona presentazione.
Grazie a tutti, grazie per essere qui. Cercheremo di far parlare quantum e arte generativa e in particolare di andare a produrre dei numeri casuali che abbiano delle caratteristiche che ci piacciono, che desideriamo per andare a creare varietà nell'ambito dell'arte generativa. Chi sono io? Io sono Iona Salviati, una presentazione proprio brevissima, sono organizer di PyRoma, sono co-leader del GDG Roma, sono VTM Ambassador, ma anche molto di più. Tagliando i titoli nella vita faccio il Solution Architect, in realtà non mi occupo di Quantum, questo è un hobby. Nel mio tempo libero infatti faccio un sacco di cose che poi mi piace condividere con la community, come ad esempio sto facendo oggi. Com'è andata, diciamo, com'è iniziata l'idea di fare questo talk? A dicembre del 2024 ero in casa, stavo passando le vacanze di Natale, sono incappata in questo contest di arte generativa che si chiama January del 2024. Funziona così, ogni giorno vi danno, diciamo, un prompt diverso, i prompt escono tutti insieme, in realtà anche con largo anticipo rispetto all'inizio dell'anno, e la regola è che questi prompt devono essere un'ispirazione per andare a creare un'opera d'arte diciamo, nel modo più libero possibile. Quindi la regola è che non c'è nessuna regola, infatti non è necessario neanche seguire del tutto le regole esattamente o affatto, e poi si può usare ogni linguaggio, framework o medium che ci piace per andare a creare la forma d'arte che vogliamo. E personalmente sono rimasta abbastanza intrigata da questo prompt del 5 gennaio che diceva nello stile di Vera Molnar. Adesso, prima di gennaio, insomma, neanche sapevo chi fosse questa Vera Molnar. In realtà ho scoperto che è stata una pioniera dell'arte generativa. Per chi non lo sapesse, l'arte generativa è arte che in questa accezione consideriamo generata con l'ausilio di un computer, quindi con un mezzo che può andare a pilotare un braccio meccanico piuttosto che direttamente sullo schermo. E, è veramente una persona straordinaria perché insomma ha usato il computer dal 1968 e nel 2022, pensate un po', alla bella età di 98 anni, è andata a pubblicare il suo primo NFT. Guardando le opere di Vera Molnar, quello che salta subito all'occhio è che c'è grosso utilizzo della casualità. Ad esempio, nell'opera che vedete qui a sinistra, che si chiama Disorder, cioè Disordini, del 1973, che è un disegno realizzato con il plotter, la casualità vi interviene nella scelta della grandezza dei quadrati piuttosto che dei colori dei quadrati, mentre invece nell'opera qui a destra, che si chiama Cut Cards, la casualità vi interviene nella grandezza e nell'orientamento di questi segmenti che sembrano un po' sparpagliati sul foglio. Quest'opera in particolare qui a sinistra mi ha colpito molto, ho cercato di riprodurla con la computazione classica, non è molto difficile come potrete immaginare, però poi ho pensato di fare un tributo alla casualità che fosse un pochino più profondo, cercando di usare il quantum computing. Non starò qua a approfondire perché la casualità quantistica è diversa da quella della computazione classica, è un tema che potete, abbastanza anche complicato, che potete poi approfondire anche alla tele da voi. Però insomma mi sembrava un buon modo per mettere un pochino a terra tutte le esplorazioni che stavo facendo in ambito quantum e usarlo per un fine un po' diverso. Un po' di Quantum 101, alla base del quantum computing c'è un oggetto che si chiama qubit, l'avete sentito prima, è veramente il building block del quantum computing. Per farla estremamente semplice possiamo dire che vi va a rappresentare una probabilità di ottenere uno 0 o un 1, quindi un risultato classico. Perché in particolare c'è questa operazione che si chiama misura, che vi fa passare proprio da un qubit a uno 0 o un 1 con una certa probabilità. Quando voi istanziate un qubit, quindi quando lo inizializzate, vi nasce nello stato 0, il che vuol dire che tutte le volte che lo andate a misurare, fondamentalmente andate a ottenere uno 0. È una cosa che si vede qui, in questa distribuzione di probabilità, quindi se lo misurate 1024 volte, ottenete tutte 1024 le volte 0. I qubit si rappresentano in questo modo qua, che è un po' particolare, si chiama circuito quantistico. Qui viene rappresentato un solo qubit che nasce nello stato 0 e poi viene misurato. Viene misurato su quella linea sotto che vi rappresenta un bit classico, quindi 1, 0 o un 1. Che cosa fanno i gate in questo contesto? I gate vi fanno manipolare lo stato di un qubit, quindi, per farla di nuovo estremamente breve, vi cambiano la probabilità di ottenere uno 0 o un 1 a partire da uno o più qubit. Vi faccio degli esempi di gate. È un gate che avete visto anche nel talk precedente, il gate X, vi inverte lo stato di un qubit, quindi se fate nascere un qubit nello stato 0 e poi lo invertite e lo misurate, tutte le volte che lo andrete a misurare otterrete un 1. C'è un gate che è molto famoso nell'ambito del quantum computing, è il gate di Hadamard, che si chiama H, non a caso, e mi mette un qubit in sovrapposizione, che vuol dire che se lo misurate otterrete la metà delle volte 0 e la metà delle volte 1. Esistono anche gate un pochino più complessi che coinvolgono più di un qubit, ad esempio il CC0, che è il Toffoli gate. Vi mette in relazione 3 qubit e vi va a invertire lo stato del qubit target solo se i 2 qubit di controllo sono 1, quindi di fatto vi va a realizzare un AND. Vi chiederete come può essere fatto l'output di un programma quantistico. Sostanzialmente è una sequenza di 0 o di 1. Che cosa rappresentino questi 0 o 1 dipende dalla formulazione che avete dato al problema. Per esempio, vi possono rappresentare un numero in formato binario, oppure possono andarvi a determinare se un predicato è vero oppure falso. In questo ambito, per generare insomma, grandezze dei quadrati e colori, a noi interessa generare dei numeri casuali tra 0 e n. Vuol dire che ci servono abbastanza qubit e quindi di conseguenza una volta che li misuriamo abbastanza bit classici per andare a codificare questi n che ci interessano. C'è una relazione che lega il numero di bit che vi servono a diciamo, il numero che volete codificare. Ad esempio, se volete codificare un bit, se volete codificare il numero 1 vi serve solamente un bit, se volete codificare 2 ve ne servono 2, se volete codificare 6 ve ne servono 3. Come si fa a generare numeri casuali in un intervallo a piacere? Dovete trovare la più piccola potenza di 2 che vi raccolga quell'intervallo, potete generare solamente numeri tra 0 e quella potenza di 2 e poi sostanzialmente però dovete scartare tutti i numeri che non vi interessano, perché tipicamente questo intervallo è molto più grande di quello che volete considerare. Vediamo quindi come si può usare Qiskit, che abbiamo visto anche prima, per generare un circuito, diciamo, per andare a realizzare un circuito che vi generi dei bit in un intervallo a piacere. Prendete l'upper bound dell'intervallo che volete codificare, calcolate quanti qubit e quindi quanti bit vi servono e poi andate ad istanziare un circuito quantistico che è fatto di tanti qubit, quanti vi servono diciamo, per ottenere i bit che vi servono, e poi andrete a mettere tutti questi qubit in sovrapposizione e poi li misurate tutti. Potete misurarli o singolarmente oppure Qiskit vi dà anche measure all, che vi permette con una sola operazione di ottenere tanti bit classici quanti diciamo, ne vengono fuori dalla misura di quei qubit. Quindi il vostro current int generator, il vostro generatore di numeri quantistici random, sarà fatto così. Userà un simulatore, perché non abbiamo un vero computer quantistico sotto le mani, insomma per le mani. Andremo a inizializzare il nostro circuito quantistico e poi andremo a lanciare una simulazione che ci darà dei bit che andremo a trasformare in numeri decimali per tante volte quanti diciamo, risultati ci servono. Quindi andremo a scartare tutti i numeri che sono fuori dall'intervallo che non ci interessa. Il risultato che otteniamo è questo qua, queste sono 2 diverse simulazioni. Ho usato questi numeri random sia per scegliere il colore che le grandezze diciamo, dei quadrati nelle opere generate. Sono molto simili insomma, alle opere originali e in realtà il risultato che abbiamo ottenuto non è molto diverso da quello che avremmo ottenuto utilizzando una computazione classica, però abbiamo cominciato a mettere le mani sul quantum. Non è molto bella l'idea di andare a scartare diciamo, numeri che non ci interessano, per cui io all'interno di questa esplorazione sono andata a chiedermi se era possibile generare dei numeri casuali ad hoc con circuiti quantistici ad hoc, quindi dei numeri che avessero delle proprietà che mi interessavano. Ad esempio, solamente i numeri pari o solamente i numeri dispari all'interno di un certo intervallo. Per capire come fare un circuito quantistico diciamo che ha questo fine, sono andata a vedere come sono fatte le rappresentazioni binarie di questi numeri. Quindi, ad esempio, per i numeri pari tra 0 e 3 consideriamo 0 e 2 e vediamo che il bit più a destra rimane sempre 0, mentre quello più a sinistra il 50% delle volte è 0 e il 50% delle volte è 1. Questo vuol dire che sul bit più a destra e quindi sul primo qubit andremo a applicare nessun gate, lo lasciamo com'è, lo facciamo nascere nello stato 0 e rimane così, mentre sull'altro andiamo a applicare un gate di Hadamard. Andiamo a realizzare questo circuito dentro al Quantum Simulator di IBM, che trovate online, e vedete che la distribuzione di probabilità delle misure che otteniamo è proprio diciamo, equamente ripartita tra 0 e 2, quindi stiamo tirando effettivamente fuori tutti e soli i numeri pari tra 0 e 3. Questa simulazione è parecchio alterata rispetto all'esecuzione su un vero circuito quantistico, perché in quel caso avremmo anche degli altri risultati che in realtà sono dovuti a un certo errore che entra in gioco su queste macchine. Stesso tipo di ragionamento per i numeri dispari tra 0 e 3. In questo caso il bit più a destra rimane sempre 1, mentre invece il bit più a sinistra cambia, metà delle volte è 0, metà delle volte è 1, il che vuol dire che possiamo invertire il primo qubit e usare Hadamard sul secondo. Se andiamo a realizzare questo circuito, invertiamo il primo qubit, applichiamo Hadamard al secondo, lanciamo le misure, la distribuzione di probabilità che otteniamo è proprio quella uniforme su 1 e 3. Questo ragionamento si può anche scalare, quindi continuando a osservare come sono fatti i formati binari dei vari numeri, diciamo negli intervalli che vogliamo studiare, possiamo applicare Hadamard o no per ottenere tutti e soli i numeri pari tra 0 e 7 e Hadamard e inversioni allo stesso modo per ottenere tutti e soli i numeri dispari tra 0 e 7. Possiamo anche cercare di fare un filtro per i numeri casuali, quindi cercare di filtrare direttamente l'intervallo che ci interessa. È leggermente più complicato, perché in questo caso dobbiamo andarci ad affidare a un algoritmo che si chiama algoritmo di Grover. È un algoritmo che in realtà fa proprio da filtro alla fine della storia ed incrementa le probabilità di ottenere dei numeri casuali in un determinato intervallo, in questo caso. Di nuovo c'è questo warning, non è garantito perché c'è comunque diciamo, uno zampino di errore che altererà un po' questi risultati. L'algoritmo di Grover funziona così, sostanzialmente amplifica le soluzioni corrette che andiamo a cercare e normalmente viene utilizzato in alcuni ambiti che sono ricerca non strutturata nei database o ricerca di soluzioni per problemi SAT e quindi noi andremo a cercare di esprimere la ricerca nel nostro intervallo come un problema di soddisfacibilità booleana. Come è fatto Grover? Due parti, un oracolo che sintetizza e quindi descrive il problema che va risolto attraverso un circuito quantistico e una parte di diffusione, che qui in realtà serve a applicare una sola volta, che amplifica la soluzione corretta. Chiaramente prendiamo un problema giocattolo, cerchiamo di selezionare solamente l'intervallo 1 e 2 tra 0 e 3 e lo esprimiamo proprio come facciamo per i circuiti elettronici, nella sua forma booleana. Quindi chiamando A e B le variabili e prendendo solo i risultati a 1, lo esprimiamo come non A e B o A e non B. Non A e B o A e non B. Per andare a realizzare un circuito quantistico in realtà non è molto pratico utilizzare questa forma, quindi ci conviene applicare De Morgan per andare ad arrivare a una forma che comprende solo AND e NOT. Lo facciamo, appunto, facciamo qualche conto semplicissimo e arriviamo a questa forma qui, che è un po' articolata, però prevede solo AND e NOT. Quindi useremo 2 qubit per rappresentare A e B, li chiamiamo Q0 e Q1, e 2 qubit per calcolare le clausole nella loro totalità, e poi li andremo a invertire perché sono legati. Li chiamiamo qubit di supporto. Quindi questo sarà l'oracolo. Normalmente in Grover si mettono prima in sovrapposizione i qubit e poi si usa un qubit di marker per diciamo, marcare la soluzione. Esprimiamo non A e B, tutto negato, A, eccolo qua, e non B, tutto negato, e poi mettiamo in AND le 2 clausole e le neghiamo. Siccome si usa fare sì l'oracolo, ma pure mettere a posto i qubit per evitare poi diciamo, effetti indesiderati dovuti all'entanglement più tardi, applichiamo prima l'oracolo e poi il suo srotolamento, l'unwinding, cioè rimettiamo tutto a posto, pronti per applicare il diffusore. E quando lanciamo Grover, vediamo che in realtà le probabilità più amplificate sono proprio quelle di 1 e 2. Quindi tutte e sole le soluzioni di questa formula booleana che individua questo intervallo. Ve lo ripeto, in realtà le chance di ottenere 0 e 1, 0 e 3 non sono proprio 0. In realtà su una vera macchina quantistica probabilmente ci saranno ancora dei numeri che escono da questo intervallo, ma li vedrete in misura molto minore che non nella distribuzione uniforme. In realtà io ho già finito, prima di lasciarvi volevo segnalarvi un po' di risorse. La prima è un articolo molto interessante di Alessandro Berti che vi spiega come generare oracoli a partire dalle formule booleane da zero, quindi è proprio step by step. E poi se volete cominciare a giocare con il quantum computing, il link a Qiskit, che è il framework Python, diciamo, forse più diffuso in questo ambito. Io vi ringrazio, spero di aver suscitato un po' di attenzione e di interesse. E sono eventualmente pronta per domande.
Grazie, molto interessante. Allora, su Slido non vedo domande in questo momento. Se ci sono domande in platea, le prendiamo. Non capisco le mani alzate o sbadini. No.
Okay.
Ti faccio una domanda io allora. Dicevi anche prima, si parlava che non siamo proprio prontissimi per il quantum computing. E volevo chiederti, uno, se hai una visione un po' futura di quando aspetta, più o meno secondo te, e qual è secondo te il campo un po' più promettente, cioè se parliamo di machine learning, se parliamo di, non so, qualsiasi altro campo che tu vedi più promettente per il quantum computing?
Gli ambiti di applicazione che vedo sono sempre quelli di ottimizzazione, quindi diciamo ricerche in spazi molto grandi, no? Anche in ambito crittografico. Prima il mio, insomma lo speaker che è intervenuto prima di me diceva l'ordine di 20 anni incrociando le dita.
Ottimista.
Esatto, perché in realtà anche diciamo, algoritmi che sono molto banali poi vanno ottimizzati. E ci sono tantissimi qubit che vengono impiegati per esempio anche solo per fare error correction, e quindi i famosi 1000 qubit sono soggetti al rumore, fanno error correction, hanno un sacco di ruoli che non sono solo legati alla computazione, e quindi in realtà diciamo, il problema fa presto a crescere di dimensione. Un po' di giorni fa mi sono ritrovata a fare qualche esperimento, pensavo di usare solo 9 qubit, ma il framework sotto ne usava 51 per fare le sue cose, per cui ho scoperto di non avere abbastanza RAM per simulare un problema abbastanza banale.
Va bene, grazie. Domanda?
Ciao, grazie per la presentazione. Hai detto più di una volta che è complicato simulare degli algoritmi standard, diciamo, classici o di elettronica e nel quantum computing perché ci sono errori e cose che subentrano. C'è in questo periodo o fino ad ora è uscito qualche algoritmo specifico per il quantum che invece non è applicabile viceversa nel mondo dell'elettronica o del computer classico?
Esistono dei casi d'uso che sono delle POC che dimostrano la supremazia del quantum su alcuni tipi di problemi. Quindi problemi che normalmente sarebbero molto difficili da risolvere su un computer classico hanno uno speed up esatto, abbastanza forte, anche in ambito crittografico, no? Sulle macchine quantistiche.
No, perché io è solo una provocazione, non è una domanda effettivamente, però trovi curioso, dato che hai pastrugnato un po' con queste cose qui di quantum, che un algoritmo così famoso come Grover includa una cosa che chiamano oracolo, che c'entra con una teoria che è ad oggi la conoscenza più precisa che abbiamo del mondo, insomma, voglio dire, una cosa che sembra, la interpreto e non so che cosa mi esce, ma...
Non so bene perché si chiami così, non ho mai investigato il perché di questa nomenclatura, effettivamente potrebbe essere interessante andare a pescare l'origine del termine oracolo.
Allora, hai detto che un quantum computing realmente poi introduce degli errori nei risultati. Tu hai usato un simulatore che invece dà sempre il risultato esatto. Ma esiste anche un simulatore che simula anche un certo errore nel risultato?
Sì.
Cioè che si avvicina più al comportamento reale?
Tu puoi configurare, passare una configurazione al simulatore, usare dei simulatori con rumore, con varie tipologie di rumori, e vedere come cambia il risultato in quel frangente. Vedrai che in realtà la distribuzione di probabilità che vuoi ottenere è alterata.
Va bene, finiamo 5 minuti prima, se non ci sono altre domande. Ti ringrazio, molto interessante. L'ultima. Prima.
Hai mai visto un quantum computing vero?
Non ancora, solo in foto.
Va bene, last call, 3, 2, 1, fine. Va bene, grazie.
Grazie.
Sì.
Okay, we're ready to start. Welcome to the last talk of the day. And we are seeing fine-tuning of large language models, so a very hot topic. Remember to ask the question on Slido, and if we have time, we can ask live questions at the end. So without further ado, let's welcome our speaker, Daniele Giunta.
Thank you,
And
thank you. Thank you, welcome everybody, nice to meet you. I'm Daniele Giunta, I'm an AI engineer at Teris Innovation Hub. And this is not my really first talk. I already held some other talks about AutoGen and how a multi-agent system can interact together to solve complex tasks at PyData Roma Capitale. And today I want to present you this new hot topic that is exactly how to fine-tune an LLM locally, showing you a practical example. So briefly, this is the roadmap that we're going to follow. So we will answer a question about why we're talking about fine-tuning large language models. We will define briefly what is fine-tuning, what do we intend for fine-tuning. Then we will move from theory to practice, and we will finish our lecture by providing some key takeaways. So firstly, why do we talk about large language models? Why do we want to use them locally? Well, the main reasons are in order to overcome what the main limits of cloud-based LLMs are. So firstly, they regard about privacy. So with local LLMs, data stays in our hands. They never leaves our laptop, our environment, our machine. Secondly, customization. We can customize our model. We can adapt our model with respect to our company data, company needs, our domain. And finally, in order to overcome cost and speed, since with local LLM, we don't have to pay any fees for API calls, and since the data and queries does not travel over servers, the response times are really faster than with the cloud-based LLMs. So what is fine-tuning? So let's think about, for example, if I ask to a cloud-based LLM, what can I do, what should I do in order to change, for example, my company laptop? Well, probably it will start by providing us a list of steps that we have to do in order to request for a new laptop. Like, for example, understand which part of your laptop is broken, and probably you have to ask for permission to your manager, then you have to write to the HR, and so on. But what if our company has specific policies? So we need to follow some specific rules
in order to request for a new laptop. Well, this is where fine-tuning comes to help us. How do we do this? Well, we take a pre-trained large language model, and we train it further. Further on what? Further on our specific data. Okay. For sure, we can use a common technique used, supervised learning, for which we provide input-output pairs. So, for example, question and desired answers. So a concrete example may be the one of creating a customer support chatbot for a retail company. So in this case, we will teach our model how, for example, we will provide some logs between the end user and how our employee would answer to these issues, such that in the end, our chatbot will behave as our best employee would do. So in the end, it is about to make the model expert in our specific context. So with this brief introduction, we can move on from theory to practice. And here is a list of some tools and services that we are going to use. In particular, we are going to use Jupyter Notebook for fast coding prototyping. Then we will use Jupyter Notebook inside Google Colab, since we'll borrow some GPUs from Google. And finally, we will fine-tune Meta's Llama 3.2 model. We will use also Unsloth, that is a cool Python package that is really good for efficient fine-tuning. And it is well compatible with the huge ecosystem of Hugging Face. And finally, we will use this tool, this service known as Anything LLM. We will use it to connect our fine-tuned LLM model to a user interface. So now we move to our Jupyter Notebook. So in this first cell, I've already installed for you these packages. Since we're running it on Google Colab, we have to install other dependencies and so on. And I've already done it for the use case. Here we are downloading the Llama model. In particular, we are downloading the 3.2 instruct model with 3 billion parameters. 3 billion simply because it is a good trade-off between the weight of the model and the efficiency. So here there are some other parameters. We'll see also later on some other parameters. I will not dive into too much details for the purpose of this lecture. So since it took some time, I already executed these two cells. And now we're going to add what is called as LoRA adapters, also known as low-rank adaptation of large language models. And in simple words, it lets our model to be fine-tuned, to be trained not on all of the 3 billion parameters, but just over a few of them, like from 1 to 10% of all the parameters. This is the initialization of the model. We are using the getPFD model function that stands for parameter efficient fine-tuning in order to use the LoRA technique. Here I'm using some parameters value that were set by default, and they are set because of efficiency for this model. So firstly, we run this cell to initialize this model. And in the next cell, we're doing the same thing, but we call it in a different way, because in the end, we're going to fine-tune this particular instance, and we will see some differences between what happens before and after the fine-tuning. So once this cell is done, here we're going to test the base Llama model. So in this case, we are going to ask a simple question, like what is Fibonacci's area? Now it's taking really much time, but it's not a problem because we have already the output for us. So here, as we may expect, the LLM, the Meta model, will answer with a long text explaining what is a Fibonacci series. So Fibonacci series is a series of numbers in which each number is the sum of the two preceding numbers, and so on. But what happens, as we were saying at the beginning, if we ask if we ask to request for a new company laptop? Well, in this case, as we already said at the beginning, it answers by providing us a step-by-step guiding on how to do this kind of task. So before you request, check company policies, review your company's IT department or HR policies. Requesting for a new laptop, you have to schedule a meeting with your supervisor or IT representative. It also provides us an example of email that we should write to our HR mail, and so on. So, but what happens if, as I was saying before, if our company has specific policies that needs to be followed? This is what we're going to do from now on. So here we're going to upload a simple data set in JSON line format. And I'll let you show it with convert it to pandas data frame just to show it. So as you can see, is a simple question answer. There are two fields, that question and answer. We can read some of them, like for example, where can I find the forms for travel expense reporting with their corresponding answer, what approves leave request longer than 10 days with their corresponding answer, and so on. So at this point, we have to format this kind of data set. We have to add the role. So we have to convert it in role, user, and role assistant format. This is what is done in this cell, and this is the output. So as you can see, it has been converted to a list or list of dictionaries containing for each role and for each question the corresponding role and content. So we have for role user the question, how do I request a new company laptop? As a role of assistant, the corresponding answer. But this is not enough, because we have to further modify this data structure. In fact, we have to adapt it such that in the same way that the Llama model was trained at the beginning. So we have to add these tags that we'll see after running this cell. So this is before the application of this formatting procedure. And this is how the new structure results. So it has been converted in a single string with some tags that identify where, for example, the text start and the end for both user and assistant. At this point, we can use the Hugging Face TRL's SFTT trainer. So that is, TRL stands for Transformer Reinforcement Learning, and SFT stands for Supervised Fine-Tuning. So TRL is a cutting-edge library that is really used for post-training foundation models. And of course, it can be used with the supervised fine-tuning. So with this cell, we're going to do this stuff. So we are putting all together in the SFT trainer by selecting the model we want to fine-tune, the corresponding tokenizer, which is the data set, which is the field that we want to use to train our model, and some other parameters that have been set by default to make the training faster and more efficient. So after running this cell, probably this cell wasn't run before, but we can go on. Okay. Probably a cell before wasn't run correctly, but we can go on. I'll explain you. There is no problem. So here, with this cell, we can see some statistics about memory usage. So it's been using a GPU with a Tesla T4 with 15 gigabytes of memory, and just half of it will be used to train the model. At this point, we can train our model not in order to let it understand both question and answer, but we will let it focus only on the answer part. Why? Because we want our model to understand the context, so all the policies that are inside our company policies, and also in order to let it understand the style and the tone of the answer. And this is what is done with this train on response only function. So like during the training, the loss will be computed only for the response part, while the instruction part will be masked. At this point, the training can start by this simple call to train function. And here there are some statistics. For example, it says that Unslot make the fine-tuning 2 times faster. There is 1 GPU used. Our data is composed of 100 number of examples. Just for a matter of time, we train our model just for 40 steps. And here we can read that among all the around 3 billion parameters of our model, less than 1% will be trained. So I already ran this cell, and as you can see, the loss value starts decreasing. So starting from around a value of 4, it decreases over time, reaching around almost the value of 1 after around 40 steps. So at this point, we can test our fine-tuned model. And we can test either by running this cell or in another way. So I'm going to show you the second way that I think is way cooler than this one. But firstly, Unslot let us export our fine-tuned model by using this function. So with this function, we're going to export the model in a format that is readable and compatible with some runner for a large language model, like Ollama 1. So I already done this for you, since it took a lot of time. And at this point, we have 2 things that we can do. Either start creating the model by running it over Ollama and using the command prompt in order to ask questions. Otherwise, as I was saying at the beginning, we can use anything LLM. So with anything LLM, we can use it as a user interface, like, for example, the ChatGPT one. And what we have to do is to go to Settings, selecting as provider the Ollama runner. It will automatically detect the large language model that have been already created. And after that, we can directly test it. So, for example, here we can ask, what should I do if I want to request for a new laptop? Now, if everything works, it will answer with respect to our company's policies, and it will not provide the long answer that we have seen before. So probably it's a bit slow because, okay, it is answering. So what we have to do, we have to fill out the IT asset request form on the internet and send it to the asset.it@fintazienda.com. We can ask for other questions like, what do I have to do if I mill? Well, I have to notify my manager and send a doctor's note via email within 3 days. Another example, maybe for example, what should I do if I want to change project team for some reason? And again, we have to send a request to the project manager and send an update to the HR manager. So probably we can read that our model understood and learned not only the context of our company, but also the style and tone of the responses based on the dataset that we provided it. provided to the LLM. So moving back to the slides, we are almost done. Here there are some takeaways. So many months ago, thinking about fine-tuning large language model was something that it was thought to be only for big companies because of resources that they had. But for sure now, with all these tools that are available for us, like the one we've seen today, like Unslot plus the Hugging Face ecosystem, it has been made more practical and accessible to all of us. In the end, as we have said at the beginning, fine-tuning large language model locally it is great for privacy, customization, and control of our data. But if you think about it, previously I used a dataset that was simply composed of question-answer pairs. So it was a really well-structured data, and it was really cleaned. Of course, it was a synthetic data, and it was already prepared for this lecture. But unfortunately, this is not what happens in real life. In fact, most of the times, our data are sparse in our company sources that can go from SharePoint sites, Google Drive, emails, and so on. So in my opinion, the hardest thing to do in order to have a good model fine-tuned is to have a good way to collect all of the data that is needed in your use case and make them really clear. So it is the part in which, in my opinion, we should all take our energy and effort on. To conclude, in my opinion, it is better to have a shorter dataset that is well-formed, well-structured, and cleaned very well, rather than having a huge dataset, but that it is completely messy. So this is the end. Thank you.
Thank you so much. Okay, we do have a few questions on Slido, so I don't know if I can ask all of them, but let's try. So the first one is regarding customization. Current language models, large language models, seem to have good results via different techniques, like RAG or instructed prompts. Could you provide use cases where fine-tuning is the to-go option over more simple techniques?
Okay, that's an interesting question. Maybe I can use one slide that I, let's say, prepared to solve kind of similar questions. So, because this is kind of frequently asked question, no? When to use fine-tuning, when to use RAG. So, talking about fine-tuning, the model learns new info and stores it internally. When you fine-tune a model, there is no need to have constantly updated data. So it's something that is static. So you have data, you fine-tune your model, and that's it. And the power also of this fine-tuning is that the model can also reproduce the style and tone of the answer. But talking about the RAG, or retrieval augmented generation, that is kind of, mostly used in most of the use cases. For RAG, the model looks up information from external sources, from external documents, in real time. So probably I will answer this question by reading this line again. It is well suited for scenarios that needs up-to-date information. So in scenarios in which data changes frequently, and also the end user needs to have up-to-date information. And most of the time, the data used is document-based. So in my opinion, if you want to have a use case in which, if you have a use case that needs up-to-date information, probably the RAG is the best solution. But in general, when we want to to know if it is better to use fine-tuning or RAG for a specific use case, I would like to answer this question with the same answer that most of the engineers would say. I don't know if you know it, but it depends. It depends on the use case, of course. So I hope that with this slide I clarified.
Yeah, I think so. This kind of answer another question that was, how do you maintain your fine-tuned model? And how expensive is the maintenance to keeping up with up-to-date data?
Okay, well, I was just said, maintaining a fine-tuned model is quite time-consuming because I was said once you have trained your model, you have it. So if you want, for example, some data that are available inside, for example, your company, you need to do again the training and the fine-tuning of your LM. So in this case, it's also better to understand if it's better to use a fine-tuned model or another kind of technique.
Makes sense. Okay, then we have, I often have problems to fine-tune my LLM with data behaving to a relational database. Do you have some tricks about that?
Data about relational data. But, probably, I don't know the specific use case, but maybe you may think to, let's say, move your data from the database to a new different source that maybe, for example, can handle better the data that then you need to provide to the fine-tuned model. Now, on my feet, I don't have a specific recommendation for this task, but we can, if you want, we can reason together later on.
Okay, then we have a few questions. So let's go with this one. In a multimodal fine-tuning, that's kind of hard to answer, but what are the best practices?
Well, let's say that it goes a bit out of my knowledge in terms that I like the fine-tuning of the classical fine-tuning with just text. Probably the hardest part in using multimodal model will be, again, in my opinion, the part of related to the dataset. So to build the dataset, because in that case we do not have only text, but we have to manage also images. So probably there would be a way to manage both of them together and to have a fine-tuned model that really fits your needs.
Okay, we have some more like easiest question. Some of them you already answered, so I won't say them. They're asking if your code is published somewhere, they can find it.
Not at the moment, but I'm going to push it on my GitHub.
Okay.
So if there is a possibility to share then the Git, I will share it with no problems, of course.
Okay, I think we have time for one more. I think so. How do you handle the model in production? Do you keep a machine always running, or do you could start it only when a new requests come in?
Well, in production, what we can do is moving for sure from Google Colab and Jupyter Notebooks to something that is more reliable. So one may think to move from local to Azure. So there is all the Azure ecosystem that is really good to do this kind of stuff. So there is Azure Machine Learning Workspace that provides you some GPUs. And in this case, you can also set, for example, some virtual private network. In that way, your data never leaves your company network. And you may also set for example, your virtual machine to be powered just for some period of time, the needed time that the application needs to run.
Okay, I think we have time for one last question. Okay, you use a tabular dataset, like with question answer to fine-tune the model. How can one build such dataset if we start with company documentations? I don't know exactly what's the...
if I understand the question, so if we start from like a PDF document in which there are a lot of company policies, we can do things. Either we employ some people that are that are in charge of creating such data sets, so they could do manually question-answer pairs related to our company policies, or otherwise we may use some large language model, so either local or some cloud-based. So starting from this PDF, please generate 100 of example of question-answer pairs that are needed to fine-tune my local model. This is something that can be done, for sure. Mm-hmm.
Okay, I think we don't have any time left, so thank you again.
Thank you. Thank you very much.